Good morning, everybody. Welcome back to the PhD workshop. I think it's time to begin. We will run with 15-minute delay, but it's reasonable. We have plenty of time to catch up during the breaks that are supposed to be long enough. So the day is full of many events. We start with an initial introduction by Fosca Gianotti today, because we wanted to have also sure that the students also have an idea of so big data, what it is. It is not an ordinary project, so it's already mentioned why it is supporting our community very much. So I asked Fosca to make a short presentation of the rationale of the research infrastructure, what the research infrastructure is and why it's helpful for our PhD program.
Okay, so very short. So this research infrastructure is named, so you may find the connections with the PhD program also by the name. It's a social mining and big data ecosystem. This is a European project within the program of infrastructure, including the e-infrastructure. So essentially is a place, an ecosystem that we are creating in collaboration with the European community that is meant to help researchers to perform better their research. And the kind of researchers we are targeting are those which want to use in their scientific hypothesis a data-driven approach. A data-driven approach based on the fact that there are big data which may be a sort of proxy of society. So those researchers, the one that we are serving, they have in mind to observe society in a variety of different dimensions, and they want to try to understand the society using the big data traces which have been left behind by human activities. There are several European partners. So, and the strange things, so it's the objective of the project is like, you have in mind when you, so we are building the cooking space for cookers and chefs coming and serving clients. So here we are cooking the kitchen, and so we are not cooking the kitchen, we are building the kitchen, so the basic infrastructure. And it is a bit strange because it is done by different so the tools that we are putting there are the analytical methods, plenty of big data analytics algorithms that researchers have built in the last 20 years, researchers of this community. And those algorithms are within the area of text analytics, network analytics, social network analytics, human mobility, and other things. The philosophy which is behind is that we strongly believe that data scientists should be responsible. So we think that responsibility is also something that needs tools and guidelines. So, and for that we have also something which is called an ethical legal framework, where we have put together, since many years, technicians to develop privacy-enhancing technology that we want to offer to to our chefs coming there. And we have also lawyers and philosophers that try to help to provide some guidelines also for the chefs and the users, such that they think a bit. Because sometimes it's better to think in advance to the possible breaks that our finding and technologies may do. So there is a part of ethical framework, so there is a big data ecosystem. Again, this is a space that's very important. This is a space where it has the ambition of saying that, okay, just to say what is it is easy to do research at Facebook. We saw 2 days ago, Facebook presenting how nice things they can do. It is easy they have plenty of data. It is easy to do research on Google. They have plenty of data. it is not easy for an economist that want to do some demonstration and does not have a demonstration, of, for example, on labor, what will be the new trend of labor, without being a researcher, a strong connection with LinkedIn, which is nowadays the platform that has more data on the labor. So the challenge that we tackled 5 years ago is to find a way, a place where data, the one that we may put together, also including the companies, those data may be offered to our chefs to do those research. It's not easy. It's very difficult because we need to involve the companies, to let them to give at least several data sets. But those are the minds that our minds that we offer. And there is another nice thing that any of the experiment that the scientists do, very often the experiment that you do or you have done or you will do, it's also a big effort in data preparation, in data cleaning, data curation. And then those data, once you have done your experiment, what usually happens is that the scientists throw away those data sets. Okay, data have been done, you have demonstrated your finding, and that's it. So the philosophy of a European community is that those data should be a resource for other scientists. So we try to promote a reusable science, such that if it is valuable, what you have prepared, what you have curated, is a resource for someone else. So we need a space such that those resources, those data are curated, described, may be founded by other researchers. So all this is to create the space where what we have done is findable. So there is a manifesto that European community in this area of research infrastructure depicted. It is called, it's a FAIR, which means findable, accessible, reproducible, and interoperable. So it is important that what we produce, both in terms of data, in terms of methods, is later on usable, findable. That means there is a findable, that means that the search engines can find. To make the search engine find, we need to have a catalog which is describing the things, all those things that usually the scientists are very bored to do this. So I have done the experiment and I throw it away. No, it is important to make it reusable by someone else. So we force our chefs also to do the effort of describing the things. And another important part of this project is that we have a program for transnational access. It's a program for supporting mobility. Mobility means that we have a big quantity of funds which are left for funding not ourselves, not the people which are building the kitchen, but for users, for chefs coming in the various places and do their experiments. We have a sort of small program for the people apply to us with a project, and this is very important for you because it's a mobility supporting mostly PhD students. So you want to spend 2 months at Sheffield, you want to spend 2 months in Finland, you want to spend, and this is completely funded for 2 months. It funds the travel and also the subsistence, up to 3,000 euros. So it's nice for moving between us, but also for having guests coming from all over the world. We had Brazilian, we had Mexican, so scientists that were attracted by the data sets that we have. They came to do an experiment on crime. They came for doing an experiment on some economic issues. Okay, and so on top of this, we have created several domains where we identify community of chefs which are interested to work on these methods. Of course, those community, it's composed also by us, because of people that we are also part of these people producing experiment there. So, and the community are city of citizens, where all the issues on mobility, understanding human mobility, understanding the towns, the territories, migrations. We have seen several experiences, several experiments those days. So some of the projects that we have seen by your colleagues of other data scientists, other PhD students, but also in the master, if some of you were here 2 days ago, were within these places, these domains. So societal debates, where all the information, so so the objective is to observe what is happening on the social media, well-being, and then there is also ethics. Ethics, again, a place where ethics is a combination of guidelines and tools, that may be inserted in our process. So here we talk in this place, virtual access means that we have this platform of resources. Each time that an experiment it's approved to be in the platform, in the infrastructure, there will be allocated storage, execution resources, and algorithms and methods that they may use and they may continue to extend. And there is this idea of this metaphor of virtual research environment. Each of the exploratory is a sort of virtual research environment, is an aggregation of resources where experiments which are of interest of that domain so the resources are aggregated according to the experiment. It's a very dynamic concept, of course. So the way you access is our e-infrastructure, which is the platform which is behind this, through this web page. You register, you enter, and then you can see, you can explore the various exploratories and find their stories, examples of use cases to get inspirations. And then there are real methods there. You can also explore the methods. So far we have around 200 methods and so resources, which is 150 methods and 50 data sets. And then there is also an e-learning area. Again, so we think that our chefs may be very coming from our community, and they sometimes may need some training for using the infrastructure, but also training on data science. So there are plenty of slides there. So far, it is in the form of slides that we have provided small courses on specific topics, which are the result of the courses that we do. We do here in Pisa, the courses that done people in Sheffield, in Alto, all the courses which are around the topic of data science. So and there you are invited to become a member, to upload. So I conclude with this one. So becoming a part of this ecosystem, it's very useful. I think it's a resource also for the PhD students, and because they can find their place and people where to work with. But also the idea is that once you have done an experiment, your PhD thesis, or even in some intermediate step of your PhD thesis, would be nice that provide resources back to the infrastructure. So the idea is that someone that wants to work with us, with this ecosystem, so far we consider the ecosystem is done also by people. It's not only the resources, the algorithm. So a person comes, there is a team that takes care of this new project, a new experiment coming there, and then the skills of the data scientists, which are so far in the research infrastructure, help them to transform their problem, their scientific challenge, in an analytical problem. So that's the cycle. Is this one? It's very new picture, which has been done just yesterday. Okay, let's conclude my talk. So this is the space that we are offering to the PhD. Some of your colleagues are already contributing. And then we have also, I see that there is also a semestral newsletter. So we try every 6 months the idea is that to amplify what we are doing and to try also to offer a space where we can also tell the story. So to have a sort of encounter between scientists and also help the scientists to tell the story in a divulgative way. And the newsletter is a tentative to this. Okay, so let's conclude if you have questions. This is the call for the transnational international access, so you can apply since now. Okay, I forgot to say the training. We are also organizing PhD summer schools. And actually, the two planned for this year, one is in June, it's a summer school completely on fake news and will be in Sheffield. And there will be one in September.
It's a fake summer school.
The fake summer school. The true summer school, it's one in September here in Pisa, where it's on data science at large, more data science at large. So, okay.
Thank you so much. So, yeah. Can put the bar on what they prefer to eat, sandwiches, salad, and so on. So we should circulate this one. And it will be withdrawn at 10:30. So do it now, basically. The second, actually, the first technical presentation is by Domenico Girasuolo, Chiara Seghieri, and Michela Natilli, who work together on GIS, Geographic Information in Healthcare Systems. And yes, please.
Okay.
The floor is yours.
Do you hear me?
No, but you can use.
Or should I use the mic?
We have the mic. Yeah.
Okay. I didn't know about the streaming, so that's fine. So, good morning to everybody. I am Chiara Seghieri. I work at the MES Lab, which is a lab within the Institute of Management of Scuola Superiore Sant'Anna, which deals with the performance evaluation in healthcare. And I'm going to present two projects. One is made in collaboration with the CNR Institute with Michela Natilli, who is actually there. And one project is about, this project is about the use of GIS in healthcare. I can use this tool to support decision making in healthcare. And another project is about the collection of data on patient reported experience. And Domenico Girasuolo is, I don't see him, but he's here. And he's one of the responsible of this, you're here, of this project. First, just a slide of background of the lab of Management and Health Lab of the Institute of Management of Scuola Superiore Sant'Anna. The lab has been established in 2004 at the school, and we have a strong experience of collaboration with physicians, policymakers, to support them in the performance comparing the quality of the care that is provided by the regional healthcare system. We created, starting from 2004, a multidimensional performance evaluation system which comprises hundreds of indicators that are monitoring from different points of view the quality of the care that is provided by the healthcare organization. And our performance evaluation system has been also adopted by other 10 regions in Italy. So we are comparing the performance of the regional healthcare system with space and time. This is our website. So if you need more information, you can write to me, either write to me or going to this website. We also of course, we collect a lot of data regarding the performance evaluation of the healthcare system. We produce a lot of applied research in order to provide policymakers with evidence-based data. And also, we, as I said, we collaborate with physician, clinician, and the healthcare management of Tuscany region and the other regions. And we are also doing training to these CEOs of the healthcare organization. Since we are working on monitoring and measuring the quality of the regional healthcare system, we created an integrated data warehouse starting from 2005. We collect different kinds of information at different levels, so both at individual areas, organization, and of course region. And with regard to Tuscany, we have access to all the healthcare administration data. So we know at individual level and we can link them. So we know for each patient or resident in Tuscany if he's been hospitalized, how many drugs he takes, if he's doing, I don't know, lab services or outpatient, he has access to outpatient services and so on. This is for Tuscany region starting from 2005. So we have time series data at individual level. As I said, we also collaborate to measuring performance with other 10 regions. So we are coordinating with still 10 regions which are responsible to calculate their indicators. But of course, we have access to all the indicators at provider level of all the regions starting from 2008. We also, as I said, we measure performance of the healthcare organization not only from the clinical point of view, but also from the patient point of view. So we we administrate survey to patients to collect their satisfaction, their experience, their reported outcome with respect to the care that they have received during the year for the different healthcare services, so hospitalization, emergency department, and so on. This is for Tuscany, and also we coordinate the surveys in the other regions. So we have access to individual level data from the patients who report their experience online with web surveys, their experience with respect to the care that they have received. We also perform survey to the employees of the healthcare system. So we have data about the organizational climate within the health providers. And the last but not the least, in the last few years, we also add the spatial component. So at least for Tuscany, we started with Tuscany, but hopefully we will add the data of other regions. We were able to georeference patients, all the residents in Tuscany, so we have their address and we could be able to locate them in the map. And of course, we were able to locate the providers in order to have information about how the patients move to get the care that they need during the year, and their distances, their travel, and also we merge this spatial data with individual information. So we have socioeconomic status, we have sex, gender, and so on. With regard to this last part, as I said, we introduced this spatial information in the last few years. So we start working also, one of our research projects, which is in collaboration with the CNR, is about health geography. So traditionally, merging GIS data with healthcare data, like administrative data or clinical registry data, has been used more in epidemiology. For instance, to examine disease rates over space or time, to identify disease cluster, mapping variation of a disease. But, as I said, we are working with the healthcare management, so we start using this GIS integrated system to measure, as I said before, the access of the patient to the services in order to support the management in planning and reorganizing the network of providers that are delivering the care, in order to assure that all the patients have the same access to the same providers, and taking also into account distances, but also personal barrier like socioeconomic status, like age. Of course, elderly are less willing to travel to get care with respect to, I don't know, younger, and so on. So we work with this integrated database, and this is our, let's say, broad research question: how can the GIS support the healthcare management in their organization, redesign of the delivery system of the regional healthcare services? We start working on this. We have already produced something, but we want to improve our methods, our models to to measure access to healthcare services by taking into account the population needs, as I said, their demand, clinical demand, but also cultural, social, economic constraints, and also, of course, geographical barriers. There are mountains, there are distances, which can, geographic barriers that can influence access to the healthcare services. So this is one project. And another project, as I was saying, and Domenico, if I'm saying something, I'm missing something, please say something. I don't know whether, because I'm not the coordinator of this project, is about the collection of data from patients. We are running web survey to patients that has been hospitalized along the year in any healthcare, in any hospitals of Tuscany and other regions. And we developed, of course, a validated questionnaire to measure their experience, to collect their opinion about the care that they have received along their care path from the beginning, when they are the first day of hospitalization, until the end, for all the phases, and with respect to all the different type of services, for instance, the care that we have received from the doctors, from the nurses, and so on. And along in these questionnaires, we also collect some their comments. So it's textual questions. Some of them are close multiple answer, and others instead are like comments. And it's a systematic survey, so it's not a sample survey, sort of census data. So we send the link with web survey to all the patients that have been hospitalized along the year in Tuscany and the other region. Therefore, we collect a lot of data that need to be, of course, analyzed. They are all, as I said, they are all stored in this integrated IT system. And we, as a lab, of course, we have this system, and we use different software with this, and we also have different expertise within our lab. We have IT, statistician, economists. We are a multidisciplinary team, and we analyze. Therefore, we analyze these different kind of data from different point of view. And this is an example. It's from Mayer Hospital, for instance, where we collect, as I was saying, the experience from the beginning, so the admission within the ward, that specific ward, it can be medicine, surgery, maternal care, until the end. And we have started already to analyze some of these data. In particular, for instance, we found that there are differences among the hospital in terms of patient experience and satisfaction. And we started working, which is the most difficult part, on the textual. We are doing this textual mining, which is the most, we collect a huge amount of data, which need to be properly analyzed, because these are textual data. And so, for instance, we start working on polarity of the comments, because these comments can be, are also displayed by the healthcare CEOs who see the comments, which are also delicate, because they can refer to specific doctors, physicians. So we are trying to find way to analyze these comments, to provide the healthcare CEOs with instruments to evaluate the care that is being delivered at their hospital. So, for instance, at Mayer, we found a lot of comments about the word courtesy is much more used at the Mayer Hospital, which is a pediatric hospital, it's more used at Mayer with respect to other hospitals, because probably, for instance, this is a pediatric hospital, so there are kids, so the courtesy of the employees or the doctors or the nurses is completely different, the way they treat the people with the other more general hospital. So this is a work in progress. Meanwhile, is something I don't know, don't remember. And yes, we need to add something? Okay. And these, of course, as I said, these are two of the projects that our lab is running, but if you want to have more, if you want to know more about what we are doing, the research activity that we are running, you can just write to me or Domenico or go on the web page of the lab to see what we are doing. Okay, thanks.
Thank you very much, Chiara. So this, as you see, the application in the health, public health sectors are very many and very challenging. We remain close to this domain by looking at genomic data analysis. Very, very important and cool topic today. We have in our board also Nadia Pisanti, who's a computer scientist working on finding ways and algorithms to deal with genomic data, and that's the topic of our presentation today. Nadia.
Thank you. So I have to warn you, I will bother you with some almost off topic, but I intend the goal of this workshop with the students also to really let you understand what are the peculiarities of each lab. So I do stress that I will show you what are the methods we use, which are not the classical data science ones, and just to let you know what we actually do in our group. In fact, I'm not really the data scientist as most of the folks are here. I don't use, for example, learning or deep learning or general statistical approaches, but more combinatorial algorithmic things. I'm actually very bad at statistics, I have to admit. So, the bioinformatics group of our department is actually quite a known story. It started more or less when the bioinformatics started in Italy with a professor which is now retired, and also on the teaching level you can see this tradition, because the very first course in master level in bioinformatics was in Pisa, and now there are several. There's one in the biology master, one in the computer science, there's a biomathematics course in mathematics, and so on. So these are the main research lines we have been developing in the past. There's work on compression, data compression. There is a work which is quite old on computing genomic distances. Another one I've been doing for a very long time is to find in genomic sequences repetitions and regularities. Another one, the red, which is actually still quite active, which is the analysis of genomic data. And that's somehow the way I do data analysis. And in particular, we are interested in detecting polymorphism in DNA sequences, where polymorphism is the variants that characterize difference between individuals. So these are the current research lines, and for a few of them I will just, as an example, show what we actually do. One is what I call pangenomics, which means to actually see the genome not as a just single reference sequence, but as a whole population, which is somehow grouped together, represented with the same object, and the objects for us are what I wrote there, the ED text. Another is to do haplotype assembly, which means directly from data coming out of a sequencing experiment to try to detect the locus in which single DNA bases are different. Another one is still out from the raw sequencing data to compare genomes without assembling the genome, and I will show what this means. And in general, detecting variants and analyze data. So we have many collaborations, so I was curious now to see, I see King's College in this, so with data. I King's College, London, a couple of Italian universities. The CWI Amsterdam was a very strong group on life science and health. The INRIA in France, and the Illumina Cambridge, which is the company, which is the leader in the sequencing technologies. So this is one of the problems we addressed, the haplotyping. The story is this. Up there you see a genome, which as you know is a double-stranded sequence. And in red are positions in which the two alleles of the genome have a different base nucleotide. And when you do the sequencing, due to biotechnology reason, you can't really sequence a whole genome. What you can do is to do the actual job of picking an in vitro molecule and getting an in silico file only for a limited size fragment. And what we have actually as data are these fragments in silicon, and you don't know actually the whole assembled genome. And out of these raw data fragments, we want to detect the positions in which there are the differences. And this is a combinatorial problem. We actually transform the data into matrix, and then we have to sort the rows of this matrix according to agreement in having the same allele with the same slip. So it's really a combinatorial mathematics algorithmic method. These are, I was very brief, but there are many results on this topic. The most relevant one somehow is this WhatsApp tool. This is the logo, which we maintain and update since 2015. It has by now more than 10,000 downloads. Another topic is what I mentioned before, the pangenomic. The idea is that we have a pattern, so a fragment. I want to map on a reference genome. And the reference genome is not just one single linear string, but rather the outcome of a suitable alignment of several genes which are related. For example, different individuals of the same genome. So this is an example of a possible text representing this alignment, where we have collapsed it into a normal string, like the T there, where all the genomes have the same value, and we put a set exhibiting explicitly all the possibilities where different genomes observe different strings. So this T tilde, we call it elastic degenerate text, is actually a way to represent a multiple set of genomes which are strongly related. And what we may want to do on this, for example, is to pick a read, a fragment coming out of a sequencing experiment, and to map it, to see where it is in the genome. So this is, for the algorithmic community, well known as the pattern matching problem, which we do on this special text. And we have a bunch of results, a very efficient algorithm to do this, both in exact way or allowing mismatches and small edit operations. And these are the recent publication on that. This is another topic actually run by my colleague Joanna. She's not here now. And this is comparing actually, this is called metagenomics, many different genomes, for example, from the microbiome of the gut of a person or an animal, or environmental genomes from the sea or from the ground, and to study the amount of diversity of bacteria you observe there. Another one is to compare strings which are not linear but circular, so you have to find the best rotation so that they maximize the similarity. This is also a recent work which was very effective. Last one, This is actually really in progress. Okay, so the idea here is there is a very strong tool in string algorithms, which is the Barrow-Squillet transform. I will try to explain what it is. And actually what we managed to do is to give a characterization of the onset in genome sequences of a variation of a polymorphism. It characterized on the Barrow-Squillet transform of these strings. And the Barrow-Squillet transform is very strong because it is a representation of the string which is very, very easy to compress, and where it's possible to do search and mapping on the compressed data. So our idea is this. Imagine there you have these three genomes, the three colors, purple, blue, and orange, where you observe what is called a SNP, single nucleotide polymorphism, that is a single position in which the three individuals exhibit a different value. And for the rest, the context, everything is the same. So now I tell you briefly what is the Barrow-Squillet transform. Imagine this word, abraca, okay? And imagine you do all the circular shift possible on this string, and you sort them in alphabetical order. That's what you do. And the Barrow-Squillet is actually the last column of this. The interesting property is that for all i's, what is on the first column is actually exactly what follows what is in the last column. So what is in the Barrow-Squillet column is followed by what is on the left, and it is in alphabetical order, which means that if you have something which is followed by the same context, like up there, in this Barrow-Squillet, they are all consecutive, and this is the characterization we give. And since you can extend the Barrow-Squillet notion to several strings, we did so, and we have a very efficient algorithm we published last year, actually beginning of this year, to detect directly on the Barrow-Squillet of genomic fragments the positions in which individuals show a SNP. Okay, I'm done. Thank you.
Thank you, Nadia. I think the question, comments, and whatsoever are left for the break. Now I have the task of introducing myself, which is, I apologize for that. The next presentation is actually in the program. I would like actually to speak as one of a pretty large group of persons that is focusing on this topic around explainable AI or explainable machine learning, including Riccardo Guidotti and Monreale, Cecilia, who's a first-year PhD, and Franco Turini. More and more people somehow addressing Fosca, addressing this topic of making machine learning models more comprehensible and somehow easier to understand. It's a topic that is really gaining a lot of the idea of developing more explanatory, more meaningful models, either because we are able to create brand new models that are not only accurate but also meaningful and comprehensible, or to make a black box model comprehensible instead, which are two faces of the same coin in a sense. It's a topic that is of increasing importance, not theoretically and not only ethically, but also for science and industry very much, because we don't really trust what we don't understand, and this is going to be an issue. Very clearly the motivation. What we are observing nowadays is really a kind of very, very fast transition from two ways of looking at coding, at how to create programs. I was born, we were born in a time where humans were coding algorithms in a very, very precise detail. Every very single step was somehow, And therefore, we have developed software engineering formal methods, many different tools to somehow test the artifact that we were creating, check their correctness with respect to requirements or expectation. Now, all this is very, very much changing very, very fast, because what we are observing is that over and over again, we are actually creating programs in a different way, by learning from examples. We have many examples coming from experience, from data, that we can collect and that we can annotate with expert annotations. And instead of really programming a tool that is, for instance, translating a language into another, just to make one example, we give up to somehow create the translator in the old-fashioned style. And we instead we create a meta program, a machine learning model that is able to be trained on these examples to create a program that is a very good translator. And we don't know very well how it actually works and what kind of reasoning it actually uses. We only know that it exploits statistical association and correlations in the data very, very well. And therefore, and this is very much the hype about AI today, the fact that machine learning models have become more and more able to exhibit intelligent behavior in the sense that they are very able to somehow recognize objects in scenes and in images. They're very good at translating or understanding natural language. We all have seen these dramatic improvements in all these tools in the last few years. And mostly this is due to the fact that we know how to learn from examples. If we have examples of tissues or, fMRI or whatever images of skin dots, we can actually use the expertise of medical doctors to label this with a class, benign and malignant, for instance, and create models that are able to generalize from the doctor's wisdom to do that in a way that can be very, very effective. But one thing is that in the end, the model is a white box, or something comprehensible, like a small decision tree that can be transformed into a narrative that, for instance, the medical doctor can understand and validate and maybe learn something out of it. And we can start a conversation between the human expert and the machine to improve. A totally different thing is that instead it's a black box, this model. For instance, a very complex deep neural network with thousands of variables, which is perhaps very, very good at doing the task, but whose logic is not really easily understandable even by expert data scientists, and therefore it's very difficult to extract a narrative, a logic out of this. And this is the issue. And why this is problematic? And if you look back into the history of data mining, machine learning, classification model, this has always been an issue. If you try to deploy a machine learning model in reality, the fact that it is comprehensible, it's a huge factor of success of the project. Doctors will adopt a method they can understand if they trust it and they are able to interact with it. Doctors will not adopt a method that it's a black box that is simply somehow there to replace the experience of a doctor with something magic that puts together the experience of thousands of doctors in an unknown way. So it's not only a matter of ethics, it's not only a matter of replacing the work of humans, it's also a matter of successfully deploying the technology in many real fields. And this is actually going to be an issue very shortly in the future for AI. If we want to avoid another big disillusion of AI, we need to have very serious tools to tackle this problem, because otherwise we will bump once again into a big issue. I will get back at the end to somehow to propose to you what are the bigger open questions that we need to face, because we don't have really comprehensive answers to this problem. Right? And just to make an example why this is an issue, maybe some of you already saw this example. No? But one thing at which machine learning models are very, very good today is recognizing objects in images. Right? This is very important technology for, say, self-driving cars or for robotic vision, for domotic assistance, or many, many different applications. And imagine that you want to, from a database of this kind, you want to discriminate wolves between husky dogs. Some of these are actually being labeled by experts with age, husky dog. Others are labeled with wolves. You can train deep learning on several thousand on this example. You can train a deep learning model that will have a huge, actually, accuracy with all the cross-validation that you like. Very, very strong accuracy. Then if you try to understand why this is so accurate in such a difficult task, I mean, if you propose the same task to a person with ordinary background like myself, the accuracy would be actually much lower than that. It would be around 60 or 70%, 70%, let's say. Why is this so more accurate? We don't know, but some researcher on this specific example developed an ad hoc explanation, and the explanation was that the better rule to find out that one of this picture represents a wolf is the snow in the background. Okay? It's not a joke. The point is that there is a sample selection bias that is very strong, where, as you see, I mean, this is, of course, it's just a kind of illustration, but in the data set, in the training set, there were essentially all the wolves were depicted in the wild during winter, and therefore there was snow, large spots of white in the background. And that was the easiest way for the machine to discriminate between the two. The machine was not wrong, right? The algorithm did its work, find the most discriminative variable very, very effectively. The point is that the training set was flawed, right? A very big mistake. And if you think for a second, it's not only, it's very, very probable to have different background condition in images, right? You know, lighting conditions, different machines, different cameras that may introduce unwanted bias in the training set. So we're really never sure when we train image recognition that we actually are discriminating on the right things or not. A totally different example is from an ethically sensitive or socially sensitive task like crime prediction. It's a big issue, right? There have been a number of natures dedicated on this, on how somehow, you know, difficult is to find ways of applying in a statistically meaningful way, and also from socially meaningful ways, crime prediction tools to help, for instance, the work of judges. Maybe some of you heard of this Compass scandal, where Compass is a tool that is being used for years in the US for helping judges to decide for parole. When a person in jail asks for a different kind of sentence to get out of jail, at a certain moment the people in prison can ask for that, judges to decide yes or no, and judge decide trying to evaluate the probability of recidivism of the crime in the future. No? And so they have to estimate this probability. This machine learning model do this kind of estimation of probability based on earlier judges' judicial sentences in the past. No? Then a team of journalists from ProPublica.org, very, very nice investigative watchdog journalism association in the US, found out that by putting together many examples, that this software, this machine learning model, has an incredibly strong ethnic bias. Black and white in the same kind of situation were assigned totally different level of risk, much higher for the black than the white, even though actually evidence on recidivism shows the opposite. Why is that? Well, again, the problem is that if we train our models on biased data, And where's the bias here? It's not only, maybe there is also some racist bias in some judges, I don't know, but the main point here is that the data set overrepresents the black population compared to the black one. If you look at the demographic composition in the US, there is 20% black people and 80% non-black people. But in jail, it's just the opposite. In jail, 80% of people is black, and the other 20% is of the other ethnicities. No? Therefore, if you train your data set in such disproportionate representation of reality, you will learn rules that somehow give this kind of social stigma as granted. No? And if you learn from, let's say, ethnically biased data, you will have an ethnically biased AI. No, it's absolutely unavoidable. And therefore, in all these examples, we need to understand this logic before we use these systems, right? Because for safety reasons, for ethical reasons, for justice, or for many different examples, and because we want to avoid to create algorithms that we don't fully understand. No? This is another example. No? If you ask what are the colors of the eyes of this animal, and you should reply they are green. These are sensitivity maps. No? What part of the image are most looked at by humans or by several machine learning models? You see, these are actually where the humans look in the picture to answer the question, and these other are examples of where some trained deep learning model look at, right? And you feel immediately that there's something weird around the story, right? And a similar example in the line below. Sensitivity maps, which are one example of introduce some level of understanding, at least in this image recognition problems of how the models work. But in general, the point is that we need to have a transparent and more responsible and accountable technology in many sensitive areas where we won't deploy AI tools like healthcare, justice, surveillance, predictive policing, autonomous vehicles, or risk scoring in general. Think all the story about evaluating the risk of people for instance, for financial purposes. Right? So it's in all these things we actually need explanation, and actually we even have a law in Europe that asks us to do that. Because in the GDPR, in the General Data Protection Regulation that it's in place since last May 2018, there is precisely a right established for Europeans that says that all individuals have the right to obtain meaningful explanation on the logic involved, I'm quoting the law, when automated algorithmic individual decision making, including profiling, takes place. Okay, so people has the right to have an explanation. If you go to the bank and you are declining your mortgage, you need to know why. You have the right to know why, even if the decision is taken by a deep learning model that no one can understand why. Okay, so we have an issue here, and we don't have yet a technology to somehow sustain this kind of right, which I believe it's very fundamental. Right? It's very fundamental because otherwise we somehow, if we don't have something like that, in US or China, you don't have something like that. No, it is also very disputed point of in the legal and ethical debate. But I think it's a very important safeguard for people because it's somehow a wall between the responsibility between people and machines, right? We cannot delegate to machines ethical decision, right? We need somehow to have the final words and take the responsibility for decisions that may impact the life of people. And actually, this is applicable not in all contexts, but in a very broad number of cases. All the one I listed because it's for all legally binding decision or similarly relevant. This is what the law says. So it's very very broad field of application. So that's, I hope I gave you somehow why looking into the problem of creating interpretable, explainable, comprehensible machine learning and data mining model is a cool and important challenge for modern artificial intelligence and data science. We have been working on somehow trying to shape the ground. We have probably the first survey, comprehensive survey, multidisciplinary in different contexts of what is the state of the art up today. And of course we have both the issue of designing new generations of transparent box that can be used with equal accuracy, with equal somehow power of machine learning as the black box ones, which is very lively area of investigation. Up to now we have seen that there is a kind of trade-off between, if you want a lot of accuracy, you go towards models that are more black box, and if you want more transparency, you go towards transparent box that are less accurate. And how to push this trade-off forward, having both transparency and accuracy is this topic here. But also there is this interesting idea of how we can actually take black boxes like deep neural networks, large ensembles of boosting trees or random forests, and create in some way families of explainable or interpretable model that can be a proxy for the black box. Very quickly, this is clearly reverse engineering, so it's a kind of software engineering for black boxes. How to look at the black box behavior from input-output and reconstruct by auditing the black box, by probing it, creating experiments to create the possibility of finding either individual or global explanation that are a trade-off between accuracy and comprehensibility. Just to give you very quickly the idea of our approach. You've seen it already in Cecilia Paniputi's work, the local approach. So we can actually not, in the first round, not aim at explaining the entire model. They can have a very complex decision boundary. You see in this picture here, the classification between two classes in the data space can be arbitrarily complex, and that's why, for instance, methods that can create these non-convex shapes like deep learning models or boosted trees, random forests, latent variable models, all these kind of complex models that are able to follow the complicated decision boundary are very complex and not understandable. But in the vicinity of any single decision, is very likely in this neighborhood that the decision is simple, right? Otherwise, if it's complicated everywhere, then we are in total overfitting, right? We don't have a model overall. So that's a meaningful approximation, and therefore you can actually look locally, create a local, we may have many techniques. We have, for instance, a genetic algorithm to create a way of auditing the black box, asking questions and getting answers in the vicinity of the specific point, and then locally build a simple model, like a simple decision tree, that is going to be simple because in the classification problem is simple in this neighborhood, and then you can, from this tree, you can create an explanation why this specific instance was classified as such, and maybe also find counterfactuals. What should change actually in this instance to get a different classification, so that, for instance, to the person that is denied a mortgage, you not only explain why the mortgage was denied, but you can also explain what should change in the next application for getting it, for getting a different outcome. So not only positive explanatory rules, but also counterfactual rules that begin to move in the causal kind of reasoning that we actually have in our minds. And I finish it. You can iterate this model. You can apply this many times for a number of examples that are representative of the entire training set, and eventually you can aggregate this. So you can go bottom up, finding way to merge together similar rules that deal with similar objects. I skip all the details here. And you can create global explanations from this local explanation that shows currently to have the best trade-off between accuracy and explainability. So you can actually have, in this way, very high fidelity, which means accuracy in mimicking the black box, together with the fact that you have a small set of rules. Well, small means in the order of the logarithm of the original training set, which is already something that goes in the right direction. So it's a really, this is just one example, and it's not a solution, but it's an array of possible different solutions, because of course you need to find ways of instantiating this framework for, we did it for natural database multi-relational data, the typical data of statistics, let's say, and databases. But of course we can do it for images, we can do it for text, we can do it for multimedia and video. No? You have to do it for classification problems or for regression problems, or for ranking, scoring. So it's a huge, let's say, search space for research to explore, to find solution. Because the point is that what's a good explanation? How can evaluate a good explanation? And good for whom? Something that is an explanation for an expert probably is not an explanation for an ordinary citizen, right? How can we evaluate that? How can we bring more and more the reasoning on the level of causality rather than association? Machine learning model work on statistical association and correlation, but we humans not. We reason on cause and effect. We try to somehow in a built-in way to see what are the effect of our choices, and we don't really think very much in everyday life on how probability and the statistics, and we need to bridge more these two links. Also because we need conversational systems. A truly decision support system for AI is not a black box that tells you yes or no, but it's a system that helps you to reason better, right? It expands your cognitive abilities to consider your problem under different viewpoints, to consider also other possible outcomes, so that by interacting with the machines, you raise the level of the quality of our decision in any field. That's AI, not a black box that can replace human accountability. So I think this is my final slide. We need really much more interdisciplinary research across not only, data scientists, computer scientists, statisticians, and physicists of complex systems, but also with psychologists, also with neuroscientists, to understand really how we can validate the quality of explanation and what is the proper way of having artificial intelligent tools and human cognition really work in tandem in a best possible way. Remember that artificial intelligence is a wrong term. It's just, it was coined in a totally different era where people were thinking that it was possible to code the intelligence into our mind. This is, let's say, the failure of the first wave of artificial intelligence. Great expectation, but big failure. What we are actually doing today is something very, very human, extremely, not very artificial, but very human, because we are actually learning from human experience. And therefore, we cannot somehow escape the problem that this kind, the wisdom that we can learn by leveraging a human experience, how can we bring this back to humans in the proper forms? And that's the message. Okay. I proceed to... If anybody more wants to have lunch here, please tick one of the boxes here in this sheet of paper. The next speaker is Fabrizio.
Yes.
Fabrizio Lillo, University of Bologna. Fabrizio is a
No, ce l'ho.
is a mathematical physicist or a physics mathematician. I don't know how to frame this.
Confused man.
And he's a well-known researcher in the complex system view of economic and financial
Devo collegare
systems.
questo?
And this is the topic of his presentation.
Yes. Okay. Welcome everybody. So, if it works. Mic. Mic. Okay. So. But he didn't, no?
No, come anche quello.
Which should I use? Okay, use this one.
Vabbè, quello.
Okay. So I'm going to talk about financial data science, which is part of the activity that we are doing in this PhD. So let me present a little bit the group within which I'm performing this research. This is a quantitative finance group at the Scuola Normale Superiore, which I'm now external collaborator of. It is composed by roughly 20 researchers. There is with strong interaction with the industry. That you see here some of the partners, and we are hosting, so they are hosting a PhD program in mathematical finance, which will change slightly name next year, going more toward mathematical modeling for finance and science. And the vision of the group, let's say, is a mixture of theoretical and empirical approach, and clearly interdisciplinary approach to finance and economics. So we do paper in, let's say, mathematical finance, physics, complex system, economics, financial econometrics, and so on and so forth, and a big interest toward big data. So the topic, let's say, of a part of the research we are doing there is financial data science, which is a new term discussing, of course, the impact of data science into the financial domain. And of course, I don't think I need to spend too much time here to explain you that the arrival of big data has completely changed the way in which the financial industry is working, both at the regulatory level, but also at the industry level, and also slower, but at a constant pace, also in the academia. So I give you a couple of examples, a nice example that are not related to what we are doing for the moment, but I think is nice. So things that you can do that were not possible to do. This is a very famous project by MIT, which is trying to measure inflation by using data from online vendors. So the idea, you know, that inflation is very complicated to measure. Typically, inflation measures are very obtained every quarter, let's say, and are noisy. Sometimes are also fake, because as you see in the bottom, some government tend to give a fake value for the inflation. So the idea is to use online selling data to have a more precise and timely estimation of inflation. And of course, this is in general about macroeconomic variable. Of course, the problem is that you have a lot of data, so you have a lot of you are able to reduce a lot the variance of your estimation, but likely, given that you are not controlling exactly your sample, you are increasing the possible bias. So one of the problems here is try to find estimators which are not avoiding this large bias that can come from the fact that you don't control the sample which you do the measurement. Another example, a very nice example, is an example of what the industry of satellite images is doing for finance. I mean, okay, we know satellite images are very important, but you can use also to do financial decision. For example, you can take pictures of the parking lots in Disney World to estimate the number of customers in the amusement park or in supermarket, or you can measure, I don't know, the number of trains which arrive in the plants in China to try to estimate the production capability of the Chinese industry. And these are companies that are selling this type of product. They're selling images or analysis of images for financial investment. What I'm going to do now is to present a little bit of some of spots of research that we have done in recent years, taking as inspiration the 5V, which are 6 of big data, presenting one example for 5 of them. Okay, and why big data are relevant for finance. Well, the first example is clearly velocity. Velocity is the velocity of data production. Data are produced faster and faster. In finance, this is extremely important, especially when you go to electronic market. So nowadays, electronic markets are extremely fast in the way in which data are produced and must be, of course, elaborated. One example, again, is a nice story, a nice example. You know, the 2 most important markets in the US are New York and Chicago. And if you want to send a signal between the 2 markets, because you want to do arbitrage between the 2 markets, you can use a fiber optics. And this takes 6.55 milliseconds. But of course, the signals, the lights or the electromagnetic waves travels faster in the air, so people decided to create a series of microwave towers between these 2 cities in order to achieve a communication between the 2 markets of 4.25 milliseconds. And so you spare 2 milliseconds of communication between these 2 markets. And this company is selling the connection between these 2 venues to high-frequency trader, and people are buying this channel, let's say, to spare 2 milliseconds of communication to be able to exploit arbitrage opportunity at 2 millisecond time scale. We did some work measuring really what is the reaction time in the financial market. I don't enter into the details. We need to use some stochastic process modeling, which is called OX processes. But this gives you an idea. This is let's say, the distribution of the reaction time of orders which are placed in the Eurex market. It's one of the most important markets for futures in Europe. And you clearly see that the peak of the reaction time, so how much time it takes for the market participant to react to a price movement, is around 30 microseconds. Okay? So this is a typical time at which the financial player might have to take a decision. Is this good? Is this bad? This is a very relevant question also for policy. We have investigated this problem a lot. We have done some work showing, for example, that the advent of this high-frequency trader has created a large increase in systemic instability. Systemic instability means that at a very short time scale, a lot of assets immediately drop in price, okay, in a very, very synchronized way. And this exactly started at the time when high-frequency traders started to trade. And this is because exploiting this arbitrage at very high frequency can create this strong destabilization effect. Variability is also very important. A lot of the models that we use in finance are models nowadays in which you cannot assume anymore that parameters are constant. Unfortunately, we live in a non-stationary world. The crisis has shown us that we live in a world when parameters are changing through time. Doing models in which parameters change with time is very, very challenging. We did a lot of research about this. It's more an financial econometric setting. So where we have models where, like in this case, the variance or the covariance of your setting is changing in time, and you have to be able to identify this. Also when what you observe is not really the truth, but is let's say there is a huge amount of noise on top of this. So you have to use filtering methods together with time-varying parameter models in order to be able to identify this setting. This is a very important problem because most of the models that people are using, even in macroeconomics and in finance, are modeled with constant parameter, but parameters are continuously changing with time. Veracity, refers mostly to the role of news, of information in financial market. Of course, information is a very important driver of the stock price movement because price should react to information. There is a lot of research. We also did something in this setting, investigating the role of information in predicting, let's say, price movement. What typically it is done is to collect a series of news which are published, let's say, in portals or in newspaper, and do what is called sentiment extraction. So try to understand in an automated way whether the news about this specific stock, I don't know, IBM, is a good news or is a bad news, and try to see if this information is able to predict financial market movement. We did a work some years ago in collaboration with Yahoo about this, try to show that sentiment alone is a very poor predictor of price movement, but if you are able to measure in some way the importance that user gives to the news, you incredibly increase the predictability of news. In other words, we are flooded by a huge amount of news, and a lot of them are essentially irrelevant, okay, or they are expected, or they are not so relevant, and only few of them are relevant. So understanding the relevance is really critical in order to be able to predict stock price movement. How do we did this? Okay, thanks to the collaboration with Yahoo, we were able to know how many people were able to were clicking on this specific news. So we were able to measure the importance of that the people gives to the news by the number of clicks that the news obtained. So now if you consider the sentiment of the news together with the importance given by the users by clicking on the news in the Yahoo Finance portal, then you can incredibly increase the predictability of the news. So again, this tells you that there is a lot of information there, a lot of news, but the real problem is trying to understand not what the news is telling, but how relevant the news is, how novel it is, how surprising it is, because this is really what impacts the stock market. Moreover, sometimes the news is also fake. Okay, we did a work recently with the group of Maurizio Tesconi investigating Twitter. You know, in Twitter there is a way of sending a tweet, let's say, containing information about the stock market, and this is done with this symbol that you see here, which is called the hashtag, which is the equivalent of the hashtag, but that tells you that the news or the tweet is about the stock Apple and not about the company Apple. Okay, and so there is a lot of also in the industry, a lot of people are designing trading algorithms which are based on the analysis and the sentiment investigation of the tweets containing hashtags. Okay, and we were trying to investigate how this is performing, and one of the things that we noticed is that if you look at the time series of tweets containing hashtags, this for example are for Netflix and Tesla, the stocks, you see that there are these huge peaks. Okay, these very big peaks, at a certain hour you have a huge number of tweets that are discussing about specific stocks. And very often in these peaks, what you find is that a lot of hashtags are contained. These are two examples of hashtags, of tweets that contains a lot of hashtags which can be high cap, meaning important companies, and other, like the pink one, which are very little relevant, not very relevant. So what we did, thanks to the capability, let's say, of the group of CNR of Maurizio Tesconi, is try to investigate which type of investor or account were sending all this bombing of tweets at certain time. They have a very good method for identifying bots, and essentially what we found is that the vast majority of the Twitter accounts that are responsible for these peaks are indeed bots. Actually, months later, our publication, Twitter closed this account, a lot of these accounts. So also Twitter realized that they were bots. And this is an example of a bot. So you see that it's not that simple to identify by eye that this is a bot. And so essentially what we found that the large fraction of the tweet peaks on low-cap stocks are likely due to bots. So you see that a lot of information that you need to denoise, you need to understand the importance, but also you need to understand if these are not machines that are trying to cheat or to fake other machines, which I think is exactly what is happening here. The other aspect that we are investigating so is instead about financial network. I think you had already some talk about financial network. This is about the importance of interaction between financial players. We did a lot of work on in this topic, especially on the identification of macroscopic structure inside financial network, which means communities or structure which are more bipartite, or core periphery, in the sense that you have nodes in the network, in the financial network, where you have a set of nodes which are very connected one with each other, and the periphery, and the hierarchical structure, which means structure where, like in the supply chain, where you have layers of nodes that are organized in such a way. This, of course, is very important for the propagation of risk. We did a lot of work with about systemic risk in the financial market, especially in interbank network. We did some work in the past in collaboration with the Central Bank of Italy. And here, the type of network are network where the nodes are the bank are lending and borrowing money one with each other. And of course, if a bank is unable to repay the loan at a certain point, then the lender will not be able to repay its own lender, and so on and so forth. And this can create a cascade in the interbank network. So understanding the structure of the interbank network and the propagation of cascades in the interbank network, or in general in financial network, is clearly a very important aspect, and to try to understand this sort of domino effect that can occur in the financial system, and of course helps regulators to control better the system, put the right regulation in place. Networks are very often not static objects, they are indeed dynamic, they evolve in time. It's very complex to model the dynamics of networks. I don't have time to enter into the detail. This is just to give an overview about the main topics we are interested in this financial data science topic. So one of the main problems is try to understand what are the determinants. So you have a network which evolves in time, and you want to understand how this evolution is happening in time, and if you are able to predict, in some sense, when the next link is going to happen. So we develop a series of models which are, let's say, can be inferred with standard, let's say, method, in such a way that you are able to model and to identify what are the determinants of the creation of links in a temporal network, but also which allow you to predict when a link is going to occur in the future. Finally, the last example is about, if you want value. This is a work where we are still in the world of finance, but in a different setting. This is a setting where you have essentially the real economy, not the financial economy in some sense, and you have the universe of companies, of firms, that are interacting one with each other through a set of relationships. Maybe a company is paying another company, is a supplier of another company, or maybe they share some person in the board of director, or they share some research and development activity. So networks do not live in isolation, of course, firms do not live in isolation, but indeed they interact in a variety of ways. And for example, if you want to understand what is the riskness of a given company, we believe it's very important to take into account not only the property of the firm itself, meaning the balance sheet, the management, and so on and so forth, but also the environment that is really where this firm lives. And the question in some sense is how much the neighbor in this network of firm, how much the neighbor of a company are informative about the risk of this company. Is there any information about the risk of the company that we can draw by looking at the network property of the company in this network? In this specific setting, this was the work we did in collaboration with Unicredit. We had access to a huge, data set of the payment between 2.4 million Italian firms in 2014, and so we know which company is paying which other company. And we have also information about the risk rating of this company, if the company is considered risky or safe or medium by the bank. And the question is the, as I said, the neighbor, the riskiness of your neighbor informative about your risks. So the idea is whether local network properties are predictive of the risk of the firm. And you can look at this at different scale. Okay, you can look at the property of the node. For example, is the number of connections, is the number of payers or the number of payees informative about your risk? Okay, or is the fact that two firms pay one with each other, are they typically the same level of risk, or on the contrary, they have opposite levels of risk, in the sense that the high risky firm prefer to have business partner with a low risky firm? And of course, community. Okay, you can create communities of hierarchies, you can identify them, and you can ask, okay, if I consider a community in the network sense between firms, are this community, let's say, uniform in terms of risk level, okay? And so that knowing to which community you belong, I can tell you something about your riskiness. The answer is yes, all these things happen. I don't have time, of course, to explain. I'll give you one example. For example, degree, the number of payers of payee is strongly correlated with the risk level. Okay, here you see the plot, where as a function of the degree of the node, the number of connection, you see what is the probability that the company belongs to a given risk level, okay, low risk, medium risk, and high risk. You clearly see that the only information of how many partners you have already give you some information about what is your risk, okay? And so clearly you can use this to understand the relationship between risk and topology in the network, but of course you can use this the other way around, okay? So you can take this as, let's say, predictors and try to predict the risk of a firm only looking at its property. This is what we did. We built a classification using 25 network predictor and some machine learning method. Try to identify whether only the information about the network and the riskiness of your neighbors can help you predict what is your risk. And the answer is yes, you are able to do it, so you are able to give information about the risk only by looking at the network property of a given firm and the property of the neighborhood, let's say, in which the company is. Okay, I think more or less this is it. So the bottom line is that finance, of course, is very strongly impacted by the data science and by big data in general. I think the two most important research questions, at least for me, are understanding what is really relevant. The point is try to find a very feeble signal in a sea of noise. I think this is a very important point, both because there is a lot of noise, but also because Dino was mentioning this, you not always have control of the data set that you are building on. So in a way, your estimator can be very, very good, but this is simply because you have a bias in the sample that you cannot control. The other important point for us is the importance of the interaction. Okay, so the network part, let's say, of the talk, we believe that the interaction part brings a lot of information, important information both for regulators, for the industry, for the academic research about how the financial system works. As you know, and this is the last point, also from an entrepreneurial point of view, there is a lot of interest in connecting, let's say, data science with finance. This is what's called the fintech, which is essentially the blending of these two fields, and which is changing a lot the way in which finance is done nowadays. Thank you.
Thank you for this. I hope I was fast enough to... Yes, thank you very much. We have one more talk before the break, and this one is about agent-based modeling for economic systems by Francesco Ramperti of Sant'Anna. We welcome on the stage.
C'hai l'HDMI?
Dovrebbe funzionare.
My name is Francesco Ramperti, and I'm from the Institute of Economics and the Embeds Department of Excellence at the Scuola Superiore Sant'Anna. And I'm going to briefly introduce you to a new stream of research that we started carrying out something like 3 years ago, 3-4 years ago. So it's something relatively recent, but something that is also kind of expanding in our institute. So basically this is the motivation of the research line that we try to follow. As you can see, there is a strange movement in the atmospheric level of CO2 concentration in very recent times. So the idea is that we are doing something strange to our planet, and we have to be careful in understanding what the consequences might be, so how this can impact both the natural, the biological system, the natural system, and the socio-economic system. And we probably have to design policies to reduce, to prevent this kind of movement continuing. So our group is relatively small. We have 3 professors that are involved at different degrees in what I'm going to present you. One ricercatore, that is me, and 2 or 3 students at the PhD or master level. And we recently contributed to a set of European projects that in some way or another deals with the problem of climate change and with the impacts of climate change on the economic system. So what we do can be divided into 2 broad parts. The first one is modeling and the second one is empirics. As for modeling, we mainly deal with agent-based models. So basically we try to model a generic economy with a lot of different agents interacting. There are firms, there are energy plants, there are consumers, there are banks. And we have basically 3 models. The first one is called DSK, and is basically the workhorse that we have, that has been developed since 20 years, something like that. Francesca Chiaramonte started developing the model. And I'll try to introduce you a little bit to the current structure of the model. Then we have a smaller model which entails a spatial distribution of the agents, so it can be calibrated on a geographical basis. And then we have a third very stylized model of a production network that is exposed to climate shocks, and we try to study how natural disasters and climate impacts might propagate in a production network. On the econometric side, instead, what we do basically is to collect data from different sources. We try to collect data on socioeconomic outcomes and data on climatic and weather variables. So for example, temperature levels, temperature variations, precipitations, and the occurrence of extreme events all around the world. And then we try to see how the movement in the distribution of stressors, of changes in conditions of climatic and weather variables might affect the movement in the distribution of socioeconomic variables. We are working on targeting certain types of natural disasters that are particularly related to climate change, and we are trying to understand how the distribution of impacts moves over time, and then we are trying to simply model how some particular kind of extreme events might impact the growth rate of an economy in the long run. The third point is that it's something that we are planning to do in the next years, but it's still very preliminary, and it is to study how this mechanism works within the agricultural sector, which is one of the most exposed to climate impacts. So basically what we do is both trying to assess the size, the distribution of these impacts, and on the other side try to design very simple, very stylized, but hopefully useful policy correction schemes. So on the impact assessment side, what we target as output variables of interest is obviously the growth rate of the economy in terms of GDP, the agricultural yields, the healthiness of the public finance, and also the balance sheet of banks. As I was telling you, in our model we have different sectors, and one of the recent findings that we had is that up to a certain extent climate impacts might reverberate also in the financial system. On the policy analysis, the literature unfortunately tries to concentrate on a single policy instrument, which is called carbon tax, which is a monetary-based instrument. What we try to do is to enlarge the spectrum of policies that can be tested in our models by considering also regulations, by considering fiscal instruments, by considering policies for the financial system. So basically how to channel funds toward the green economy, for example, and how this might induce or reduce risks for the financial system. And finally, we are also trying to develop a mission-oriented approach, very in line with the work by Mariana Mazzucato and the proposal by Ocasio-Cortez of the Green New Deal. And we are trying to test this kind of mechanisms within our macroeconomic models. Sorry. So this is the model that we have, a very schematic representation. What you see is basically a sort of network of different agents in an economy. As I was telling you, we have different types of agents, and in their activities they also produce CO2 emissions. We are modeling an economy either at global scale or an economy that tries to mimic the behavior of very large national economies, for example the US. The production of CO2 emissions obviously impacts the dynamics of the atmospheric concentration of CO2, and so what we have is also a second model which is linked to our economic model, and this is a model that mimics the functioning of a carbon cycle. So basically we have these exchanges of CO2 between the biomass, the atmosphere and the oceans. And the outcome of this model that opens the floor to different degrees of complexity, obviously, is in the end a change in the atmosphere, the equilibrium concentration of CO2 in the atmosphere, which impacts the temperature. And associated to a movement in the temperature, what we have is the production of endogenous climate impacts to the economy. And this is the part where the modeling is most important, because it's really difficult to characterize how the economy reacts or agents react to variations in climatic and weather variables. As for the economic structure of the model, as I was telling you, we have different sectors. So basically we have capital good firms that are producing machines, basically, and they conduct R&D. We have consumption good firms. They basically produce goods that are then sold to the households. Households consume, and on the other side they provide labor to these two sectors and also to the energy sector. So the energy sector is another part of the model. You have different kind of energy technologies, moving from oil plants to photovoltaic and hydro. And finally, you have a financial system that basically provides credit to the economy to allow investments. So when firms are internally constrained in terms of financing, they can have access to external funding through credit. What we are working on now is the development of links between the financial system and the energy sector. Then on the, let's say, more physical side of the model, we have this climate box that I was telling you can have different layers of complexity. It takes as input the emissions and it gives back shocks that are modeled at the individual level. So while in the literature the standard approach is to model shocks at the aggregate level, so basically try to regress GDP on temperature, you get the impact and you calibrate your damage function in this way. What we try to do is to target impacts at the level of the agents and to see how the interaction of the agents in the network that was in the slide before emerge in terms of macroeconomic dynamics. So the impacts are endogenous, and also the macroeconomic effects emerges from the interaction of the agents. So a preview of what we already did with this model. So the model needs to be validated. The model is quite complex. It entails dozens of parameters. So what we do to validate the model is to target scenarios that are quite common in climate research and to modify the values of the parameter in a way we can get the dynamics that are characterized by the scenario, and then we try to check whether the model reproduces stylized facts that characterize the empirical functioning of our economies. So we try to see whether the empirical irregularities of our modern economies are matched by the model. Then what we did is to study the effects of economic impacts. So what we do find is the emergence of tipping points in the dynamics of the GDP. This is something that is in contrast, again, with the literature, which provides estimate of GDP damages just in levels, basically saying that what climate is doing is just to affect the level of the potential output we can achieve. To the contrary, what we find is that climate change might impact the very direction, the very growth trajectory of our economy. We find that different kind of impacts have very different effects on the emerging macroeconomic dynamics, so there is an important field of, an important scope in modeling the damages at the micro level. And finally, as I anticipated, we also found that by inducing cascade of failures, climate shocks and extreme events, most importantly, can have an impact also on the financial system. Win-win pathways are possible, so we don't have to be excessively pessimistic, meaning that it is a problem that we need to solve. But for example, our models tells us that if we are able to mitigate enough and to adapt enough, we can move the economy towards new growth trajectories characterized by new technologies. And finally, as I was anticipating, carbon price is not enough. Carbon price is the standard policy instrument. Everybody is focusing on carbon pricing, but it is of very difficult implementation, and it is not enough at current levels to produce reasonable results in terms of impact mitigation. What we are doing now, first, the modeling link that I was telling you before between energy and finance. Then we are improving the estimates of the micro-level damages. So we are trying to run an econometric exercise to understand how agents might be affected by climate change and weather events. We are including an agricultural sector. So basically, here we are imagining also an agricultural sector that provides food to the households. And then we are trying to test various types of policy combinations. Then we have also a smaller model which is called AgriLove. Even though everybody pronounces it as AgriLove, we have to change the name probably. This is a much smaller model. So we started with the idea of building up a cellular automata model. Then we complicated it to account for more realistic behaviors of farmers and farmers' interactions. And here you have the possibility for farmers to adopt novel technologies, and what we imagine are adaptation technologies. And what we try to do also is to understand the extent to which this technology might diffuse thanks to behavioral policies and under different regimes of the technology adopted, meaning under different regimes characterizing the distribution of conventional versus sustainable agriculture, which might interact with the adoption of technologies and practices that are more or less prone to deal with climate risks. And we are also inserting a climate box here in order to study the effects of climate change, and in particular extreme climate change like heat waves, on the production of food. On the empirical side instead, we are working on basically impacts, not policy right now. This is taken from a recent paper we are finishing, and it's about the distribution, the movements in the distribution of natural disaster risks. So even though in the natural science there are a lot of contribution basically telling, wait, we have to be careful, the distribution of our structure is shifting to the right, there is a bit more on debate on what is happening for the impacts, for the economic impacts of variations in the climate and the weather. What we do find is that also for the economic impacts we can observe these variations, and unfortunately the literature tries to identify these impacts through simple regression on the mean. What we show is that by adopting very simple and alternative econometric frameworks, for example quantile regression, you immediately get that the right tail of the distribution of damages is fattening and fattening over time. Interestingly, the area where these damages are found to grow most is not the tropical region, where actually these damages are impacting society and economies more and more, but is the one of temperate zones, meaning that our adaptation capacities are not as good as we might think, and also that the standard way of modeling adaptation through the level of GDP might entail some problem. And temperate zones are basically Europe and the US. Then we're also trying to understand how these kind of impacts might affect the economic dynamics, and this is done by basically geolocalizing all possible events of interest. Here you find storms in the US, and then we simply try to understand what is the link between these events and economic growth. And we do this at the very beginning through a very simple econometric framework in a panel fashion. And what we found is that even considering storms that are not extreme events, so extreme events are hurricane, but from a meteorologic point of view, storms are a medium-sized event, we have a permanent effect on the long-run dynamics of GDP. Basically telling that even in the US, which is the most technologically advanced country with the reference economy for the world, where also you find a lot of policies, really a lot of policies trying to cope with natural disasters, in the long run, an additional storm might have an impact which is not recovered by the GDP. So you have a sort of hysteresis in the dynamics of GDP. You are forced to be below the level of GDP that you have had without the storm. You are not fully recovering. And there is a debate in the literature on whether these kind of events might instead spur growth through a sort of build back better mechanism. What we find is that no, so we have to be very careful about that. And this is also done in order to improve the representation of the damage function in the larger model. So all these empirical studies are carried out in order to improve the representation of the links between movements in temperature and the way we model shocks to the economy. And this is it. Thank you.
Thank you, Francesco. Very interesting presentation. So we are running half an hour late. It's not too bad. We have time to recover plenty of time to recover during lunch break. I would say we stop for 15 minutes. Let's say we reconvene back 11:20. Okay, for beginning in time the lunch break.
abbastanza comprato style queste mail.
Come lo spacco dalla
No, però che se devi far finta di essere lui, non so che sia. No, non mi filmo io.
Quindi la black box ti consente di generare i fake data e quali sono degli meccanismi per leggerli. Questo creerà inevitabilmente accuracy e nella questi esempi di interpretazione a seconda nei quindi quella scelta lì piuttosto che questa scelta si generare queste surfaces con i generi possono avere variabilità diversissime a seconda non c'è smoothness, non c'è smoothness, possiamo generalizzare. Locale che non esplode, cioè che non dà una spiegazione tutto questo, quante feature ci sono dentro, ovviamente perché voi generate con la black box per cui fate noi immaginiamo di poterla avere vista e che è veloce tra l'altro poco costoso. Avete mai pensato di metterci sopra un errore?
No,
Fai conto che
questa
puoi
roba è agli
a un
inizi,
certo punto
Francesco.
valutare, cioè mettere diciamo così una banda di confidenza intorno a questa ricostruzione, no? Che ti accounts also for the fact che qui sei più accurato, qui sei meno accurato, eccetera. Siccome generi appunto da un meccanismo, chiamiamolo deterministico, che è quello del black box, potrebbe essere utile.
Questo.
Penso di sì, se lo può aprire un attimo.
Che multitasking c'ha un limite.
No, capisco perfettamente quello che dici e
Rigenerati
credo
della
che sia...
variabilità, capito? Cioè
Sì, sì.
la vera risposta all'intorno è quella della black box, più però un pochino di meccanismo stocastico che potrebbe modificare. No, queste sono cose interessantissime e tra l'altro veramente la roba lì è necessaria e potente in un sacco di casi.
Io il fatto per cui vedevo, toglio pure, il fatto per cui vedevo interessante questa cosa qui anche proprio per questo, no? Cioè perché secondo me possiamo provare a fare cose insieme.
Dobbiamo lasciarci un po' di tempo per fare qualche domanda dopo. Perché
il problema è che sono venute, hai visto,
no,
50.
No, capisco. Tanto
Mi è toccato organizzarlo come un TED Talk, capito? Perché se ne veniva di meno era
certo, c'era più
con
spazio.
così tante è una carrellata di robe.
Nella primavera io cercherò di fare una sorta di cosetta di evento per il primo compleanno del Dipartimento di Eccellenza.
Cominciamo?
2 minuti, 2 minuti.
2 minuti. Questo? A parte io preferirei stare in piedi, no, è uguale. No, vabbè, è uguale, va, sto qui. Va bene anche a sedere, forse è meglio. No, allora in piedi. No, casomai loro si addormentano, io sai. Però forse la mia voce si sente anche così? Can you hear me? Yeah? So, questo lo spengo. È spento. Ora? Sì. Vicino? Così? Mhm. Ok, direi che facciamo la verità. Allora, continuiamo la giornata con questa sezione ancora un po' mista di cose, di approcci diversi alla data science. Abbiamo la professoressa Monica Pratesi che è una statistica e quindi ci darà un'altra prospettiva di visione, di metodologia e di problema, che è interessantissimo. Poverty, misuriamo la povertà.
Thank
Aboliamo la
you.
povertà.
Shall I use English or Italian? What do you prefer? English. So, so Dino said a very important thing, that is the ultimate goal is combating poverty, and we should say eradicating poverty. This is the first sustainable development goal, as you probably know, in the Agenda 2030, and it is a sort of mission, I would like to call it like this, that involves a deep interdisciplinary work and the cross-fertilization of different research fields. I am Monica. You see here a list of names. They are involved in the Dagum Center. Both of them are, everybody here is very passionate in measuring things because they are statisticians, applied statisticians to be honest, some methodologists, but mainly I would define myself as an applied statistician. The average age of the group is not so high, about around 40, but many of them, 2 of them at least are young, and they are sitting here, Francesco and Gaia. So there are associate professors, Giusti and Salvati, researchers, Vincenzo, and junior researchers, we call them assegnisti, like Gaia and Francesco. They are part of the team working at the Camillo Dagum Center that is qualified as a center studying advanced statistics for the equitable and sustainable development. The center is at the University of Pisa, but it is an inter-university center involving both Florence and Siena. So the 3 main public, I would like to call in this way, universities in Tuscany are cooperating to the center. And they are cooperating through their departments where statistics is present. Florence is a department of excellence in studying statistics using new data sources, while Siena and Pisa are better qualified for applying economics using quantitative tools. Okay, there are aims. I have listed them here, but if you want, you can consult the website of the center and jump this step, because the aims are obviously many, not only promoting research, but also fostering multidisciplinary cooperation. And we are working through research grants, because we are not funded by the university. So these research grants are obtained through bids of the European Commission mainly, but also with agreements with the National Statistical Institute, our National Statistical Institute, that is the ISTAT. So in this sense, you can justify the current research program that is called Maxwell. Maxwell means making sustainable development and well-being frameworks work for policy analysis. A very long title. Generally, these titles are made in order to have good acronyms, so people can recall. Maxwell is something that you can make in something good, making something in the good way. And what we have here is the aim to go beyond GDP. So from the point of view of economic theory, we are working in the SEM-F2C environment, going beyond GDP, producing indicators that are a set of indicators that is useful for policy making. This is not given for granted. And I have had, together with Dino and Fosca, many experiences where we are working hard to produce a number, defining many indicators, very complex, also meaningful and challenging from a methodological point of view, and then the stakeholder, the policy maker, is simply deciding on the ground of other things, not of the numbers we have produced. So in this project, we have the final goal of doing something useful, a dashboard, in quotes, useful to policy making. And combating poverty is one of the, I would say, background important themes of the project. But specifically, the PISA team of the Dagum Center is working on small area estimation methods. Yes, because we are interested in big data and small areas. This seems a sort of antinomy, but it is not. Because the challenge is predicting values at local level. And when I say local, I say the places where people live. This is a definition of local I like, because it is a sort of cross-cutting definition, the places where people live. And in this, I think that the so-called big data, even if I don't like to call them like this, because they are modern data produced with current and modern IT methods, they are also big in many sense. But as a statistician, my final goal is to use the data we have. And data means given by somebody else. So there is a challenge also in discovering the data processing model and to use it in order to have meaningful and accurate estimate of poverty in our case. At a very low geographical detail, because at low geographical detail, official statistics, current surveys are not so useful. This is because they are conceived in a traditional way that give very big importance to the sample size. And as interviewing and collecting data is a time-consuming and costing activity, they tend to have small samples. And a sample is small when it is not able to give you significant, in a statistical sense of the word, estimate for the, I would say, area, if you want, you are interested in. So this is called this is the so-called small area estimation problem. So we need to predict values. This is why we started with Fosca and Dino several years ago to find out ways of introducing big data as covariates in prediction models. And this is why here you find in bold investigation of use of big data and model-based estimation. And now we are interested in another activity that is based on the data you have, I think, had described yesterday by Alessandra Righi. They are official, in quotes, statisticians claiming for this. And it is including, oh, I'm sorry, including, come back, okay, including the data on the cost of living in poverty indicators. In few words, now we are interested in using this scanner data from gross distribution to see how we can integrate with the traditional collected data in order to have an acceptable, by policymakers also, measure of cost of living in order to accompany the poverty measures that we have. Poverty measures generally are very simple. The first one is a rate, the percentage of individuals or households below a fixed poverty line. And line that is on the income distribution or consumption expenditure distribution at a local level. This is not trivial to find out how income is distributed at the local level or how consumption is distributed at the local level. I mean, sources are many, but what is our job is integrating sources to exploit the data in order to have significant estimates, so significant to be used as public data. And this is the jump that we have to do together. So I have not prepared here slides on the models, slides on the data generation, the data generating process, the type of big data we can use, because I have not an hour and I don't want to bore you. I want only, my only goal is to give you an idea of what we are doing and to invite you to cooperate with us and also to do the revolution that we are trying to prepare, or the evolution of introducing in official statistics also this so-called big data or modern data. It is a long story. And okay, one of the first results we have is the poverty mapping. Yes, because we have said combating poverty, eradicating, eliminating it. But if we want to keep the poverty issue on the agenda of policymakers, we need to produce evidence. Evidence is something very questionable many times. So what we need is to do all the efforts we have in mind to do in order to have a meaningful poverty mapping. It is easy to say, but not easy to do, and not easy to interpret. And I have a sentence that it is helping me in many situations when I am doing applied work, that is garbage in, garbage out. So it is very important to not having garbage in the data production process and in the model-based application we are doing. Otherwise, the results are not interpretable and are simply an exercise useful for an academic profile, for being famous in some conferences, but it is not the ultimate goal that we have as the center. Here we have many methods behind. I must be honest with you. So now I'm giving you things in a very, I would say, colloquial way, but when we are talking about functional data analysis, stochastic processes, and also small area estimation, prediction, inference, Bayesian tools, MCMC, and so on, we need techniques, we need mathematics, and we need this ability of applying to the data and producing results. the beautiful results that you have already seen. I mean, many before me have produced wonderful pictures and a very good representation of econometric models. I have not done here, but behind we have these problems. And then coming to this exercise on spatial price indexes, I don't want to bore you because I know that you have already seen the last presentation by Alessandra that is more expert than me on this. But I would like to open your mind to the fact that it is useless studying poverty without having, and I'm saying something terrible, a good estimation also of the cost of living. Economic theory can say hundreds of words under this title, but without meaningful data, the problem is without any solution. It is a matter of fact that having 1,000 euros in Sicily is very different than having the same amount in Milano. We know it. This is true at a small scale because Sicily and Lombardy are a small scale in comparison with Europe, but it is true also comparing Italy towards other countries of Europe. It's true at different scales. And the idea is using this modern data sourcing in order to complement the traditional way ISTAT is using to collect data on prices and quantities. Prices and quantities and sold quantities are data obtained using current surveys, sample surveys. So there is a very big jump to do, but we are training persons and using tools in order to do it. But we must be honest and say that these retail trade data are not covering the universe, because persons go to the local markets. Open your eyes. We go to the supermarket and we buy many things, but supermarket is not offering credits. Is not giving you the goods if you have not money with you. Money can be cash, can be cards, can be something. But poor don't go to the supermarket very often. Maybe they go to the local markets or to the shops because they can have things without paying anything. So problems are many, and not only related to this cost of living problem. We are now addressing another research path that is on the study of educational poverty. Always poverty, but in this case we are oriented on studying and measuring, because for us studying means measuring, first of all, poverty in education. It is not clear the nexus between economy, economic development and richness and income and educational poverty as the low skills, measured as the low skills each individual has in math and literature, but not only. It is the access to the cultural offer that at the local level you can have. So the final objective is to do the study at a sort of macro level, not at individual, macro level domain of study, that is the area again. So the small area problem is again present because current surveys invoked to measure the different dimensions of educational poverty, especially the digital dimension of it are very poor. And so we have to explore new vulnerabilities in local communities along this direction of research. I have no time more. Okay, so EP is a complex and Latin concept. We are exploring it to define it better, together with also other important actors like Save the Children. We have a good cooperation with them. But then finally, because this is important, because we are not the ISTAT, but we are involved in a laboratory, LabIn, that is a laboratory of innovation that is allowing us to have the access to the microdata and to go on in this double checking of modern data sources and the traditional data sources in order to have the final estimators we like. Okay, I think that's all, and I thank you very much for having listened to me.
Thank you. We learned that measuring poverty is very challenging because actually I also read that from United Nations that the problem is that the poverty is that actually many poor people are not accounted because they do not have. I mean, that's not produced data, so that's so it's the measure that we have worldwide. They are very much underestimated.
Yeah, and the other issue is that poverty must be, according to me, studied in the inequality context, because generally we have an idea of the poor as somebody who is not easily trackable or whatever, but instead in Italy now we are starting to count as poor also the middle classes, the so-called middle classes.
Another point is the fact that actually poverty is a relative phenomenon.
Yeah.
It's not. We cannot have a same rate, same numbers for any country. And this is it's a challenge.
It's a challenge.
And
yeah.
of course, you said poverty,
digital,
cultural poverty.
Maybe
there are more data. That something can be done.
Can be done. Okay.
Okay. Thanks very much. Now we move to complex system community again. So we are statisticians now. Complex system is information entropy network. So Diego Galaschelli from IMT Luca.
Thanks a lot, Fosca. Well, good afternoon, everyone, or good morning still. Well, I'm going to present part of the research that we do at the Networks Unit in IMT Luca. I'm also partly at the Lawrence Institute of Leiden University, and there's actually collaborations that are ongoing between these two groups. So first I would like to sketch very briefly what the vision, in a sense, of the research that we do in relations with data science is, and then I'm going to present a number of applications, so which also includes a number of projects that we are doing and possible also PhD projects on the topic. Well, of course, as we all know, I mean, say that the big data era means that there are bigger and bigger streams of data that are available, but they are not necessarily more informative. So bigger is not necessarily more informative for a variety of reasons, because data may become noisier as their size increases. Also, they may become biased, as we have seen also in some examples that Dino presented to us. So if the training set is biased, then the bias will perpetrate, right, and will affect also the interpretation of the following streams of data. Physicists, all of our group at IMT, the Networks Unit, we are theoretical physicists by training. So when we say we need a principled way to do something, we need a good theory. Okay? To filter out noise and mine significant information. So of course, data mining is in a sense also what physics has been doing for a while along the centuries, right? So to get rid of the inessential details and mine the real piece of information which is connected to the mechanism that one is about to study. Okay, so we need to identify new emergent laws, in my view, that are due to the fact that as the size of a system gets bigger, then the nature of the laws of the robust empirical patterns that are present in the data may become stronger as the size grows, but they are of different nature than the microscopic patterns that we often try to look at. And then this is clearly spanning a number of topics in data science, but in many other disciplines as well, like pattern detection means singling out relevant information once you filter out the noise. Data validation, so how can you build up statistical tools to validate the data. And then to reduce the data, I mean, which is different from compression in this case. What I mean by this is that if you realize that in a large system that you're studying, where you have a lot of data to analyze, then a lot of this data is not relevant for the behavior of the system, at least for the relevant behavior you're looking for. This means that you can also discard part of the data. Okay, so you can reduce the data, not just compress in the sense of error-free coding, so that you can, if you want, you can then reconstruct the full data set before. You can actually get rid of part of the data set. And also data modeling. I mean, when you have a pattern, then it's the right moment to build a generative model or an explanatory model for this. So I'm now going to make a few bold statements. Well, in a sense, physics is a data science by construction, right? By design, because it's this never-ending adaptive feedback loop between theory and observation, right? And this is the core of the scientific method, which is common to all disciplines and should be common to all disciplines. But somehow, through history, physics has been a champion of this approach. So in a sense, we would say that there is an in-sample part in physics, which is, well, given the available data, you want to construct a model that can explain or replicate the data in sample. But then once you have a model, to really trust the model, you want to make predictions out-sample. So predictions about data that you haven't collected yet, that have not been generated yet. And then you go to collect this data and you verify whether the model made a good prediction or not. If the model is no longer supported by the new data available, you should then adapt or generalize the model itself. So there is this never-ending loop. And I would say the moment where the model fails is actually the growth moment in science, in physics. It's when your model fails. So that's also a warning, right, with respect to this idea of training a model on some data and then be confident that the model itself will remain true with new observations. So it's very important to update kind of online this feedback and this support provided by the new data to the old model in a sense. So in this sense, in physics, but as I said, it is not only, it should not only be the view of physics. There's no theory without data, and no data makes sense without the theoretical context. Okay? So through the centuries, I mean, mathematics has been described as the queen of all sciences because of the fact that it provides mathematical tools to build your abstract model of reality, but it can't work in isolation. Well, in principle, it can work in isolation, but then it's no longer a queen. Well, it's a queen of an empty kingdom, right? Because it would be detached from reality. And in this sense, over the centuries, so starting with statistics and now data science in all its many facets, has been the servant of all sciences, where servant doesn't have any negative notion here. It means that it's been providing service to all the other sciences that, being experimental sciences, need ways to properly process the data, clean the data, interpret the data, model the data, and give this knowledge back to the different domains. So there is no, data science itself is not producing the data, right? It's receiving data from all other disciplines. In this sense, it's the servant of all sciences, and it has to do a good service to all sciences. So well, if we match this with the scientific method approach followed by physics, in a sense, physics has been concerned with providing the trust between the queen and the servant, right? So you need trust to be there between the area of mathematics that provides the abstraction and the data science, which provides with the data such that there is no longer an abstraction in place, and such that this becomes a proper description of reality. So I think this is where, this is why, I mean, people like us in our community of statistical physics believe that there is a connection between physics and data science. And when data become big, then there is a branch of physics in particular, which is statistical physics, which is the physics of very large systems that becomes playing an important role here. And in particular, I mean, we know that in many cases, when the size of the system becomes big, you lose, well, the relevance of the details becomes fainter, okay? So you may spend a lot of time in figuring out the microscopic laws that govern particles, for instance, but once you put all these particles together in a big box and you have a gas, then the bigger the box becomes, so the more the particles you have, the more complicated one kind of description becomes, but the simpler, a totally different kind of description becomes. So you have the emergence of the laws of thermodynamics, which are precise laws, that is possible only when the size of the system is big enough. So there is this idea in statistical physics that bigger is not only a curse, it can be a blessing, and actually the gray areas in between is when you have a system that contains a lot of elements but not so big such that the statistical laws of thermodynamics become reliable on that system, okay? So I mean, and this is also something that we know from probability theory. I mean, there are laws like the central limit theorem that provide precisely this kind of trust in the fact that the more you have, the more you can average, the more you can combine, the more stable some emergent loads become in the system. Okay, so there is this idea that microscopic details are washed out, so there is information loss, and this means that in a big data problem, there will be a lot of data that won't be relevant anymore. But at the same time, there are conserved quantities, and physics is a theory of conserved quantities in the end, and how you can use conservation laws to describe your system, right? So, I think that this is why physics can be fruitful in the big data era, and I see that also in the computer science community, these ideas are now becoming important. So, for instance, there is this recent article that I found, which is precisely building on this idea that the curse of dimensionality, so the thing which affects statistics and data science in many cases, may become a blessing. So, when your big data is really big, new emergent laws of probabilistic and stochastic nature generally emerge that can be used even to achieve a drastically simplification of some machine learning problems in high dimension, for instance, or to correct legacy artificial intelligence systems. Okay, so and this is explicitly drawing on an analogy that is present in physics when going from, say, physics of microscopic particles to the statistical physics of large systems. Okay, so what we do in particular, and here I start giving just a few snapshots of research topics where we are active. We work on networks, and I'm sure you've seen a lot of other talks on this. We work on networks because of their ubiquitous presence and because of some irregularities that is quite striking. So, and precisely in the spirit of identifying relevant patterns at the macroscopic level, which have to be independent of the details, that then physics becomes effective in studying the system. So, very different systems appear to be organized in similar ways, irrespective of their details. So, and they are very different from regular lattices, for instance, and they are ubiquitously characterized by this heterogeneity in the number of connections of different nodes. So, this has a strong dynamic effect. So, if you think of how the epidemics, how epidemic diseases used to travel, to be propagated over the centuries, so the Black Death really propagated like a traveling wave across Europe. Why? Because people used to walk or go by horse. And so there is actually speed in this wave of disease that you can also measure. But when you look at how the epidemics are propagated way that today you see that these are completely different pictures. It's patchy, it's bursty, so you see a disease happening in one place of the world and then immediately appearing at the other end of the world, because it's now mainly being transferred by the airport network. So, which means that a lot of mathematical tools that make sense in the case where you can embed these systems in a regular lattice or grid and then study them is in a simplified way, in terms of waves, for instance, are no longer possible. It's no longer possible to use the same tools in this completely heterogeneous setting. Okay, so a lot of things that we do is providing methods for having good null models of these systems. What is a null model? When if you want to detect a pattern, if you want to mine significant information out of a big data structure, like a big adjacency matrix or adjacency list for a network, ideally you want to find out what are the relevant nodes, what are the relevant group of nodes, whether there is community structure, whether there is some core periphery structure, as also Fabrizio Lillo was mentioning before. Well, this would be very easy if your network were regular, like a lattice. So you notice the formations from some reference structure you have in your brain, which is a flat space, in this case, so a regular lattice, and it's very easy to spot where the pattern is, okay, a massive body in this case. But try and do the same for a completely heterogeneous structure like a complex network. So here the reference of a lattice is completely misleading. So you should not expect objects like the internet to behave like a lattice. And then if you don't have a good null model for how this network should look like, you can't look for deformations or patterns of relevant structure. So we do a lot with using principles of information theory and statistical physics, and especially the maximum entropy principle, to provide good null models of how this heterogeneous object should look like. So we basically start from a real system and then construct a null model, which is a statistical ensemble of possible networks that have some built-in constraints. So something you realize is robust in the real world, and you then put it into your model. And this provides a new reference frame for spotting interesting structure. Okay, and then similarly, we do a lot of network reconstruction, but here I'm going to be very quick because Tiziano is going to talk about this later. Well, mainly the goal is when you don't have access to the full structure, for instance, because of privacy issues or confidentiality issues, like in an interbank network, but still you need to have a good, reliable estimate of how the network looks like because you want to run some dynamical process like a stress test on the network. You need good tools to reconstruct the structure. And again, maximum entropy is a very important and effective tool in this case. And by looking at the theoretical side of it, you see that this construction of systems with constraints is again an ordinary tool in physics, in statistical physics, where we have this idea that once you want to impose some feature on your system, like a given number of links on your network, or a given number of links per node on your network, you may take the hard way, so you may impose these constraints in a sharp fashion, in a hard way, so giving zero probability to all the configurations that are not compatible with your constraint, or you can be soft, so you may accept other configurations as well, provided that on average over the ensemble, then the expected value of the property you're enforcing coincides with the observed value. And for many years in physics, people believe that these two constructions are asymptotically identical in the sense that when the system becomes bigger, it makes no longer any difference which way you're taking. Actually, we noticed that this is no longer true in real networks and other data structures that have the property of being heterogeneous. Meaning that you have constraints at each node of the network, for instance, which is typically the case. So each node as since these networks are very heterogeneous in terms of node degrees, for instance, each node needs to have its own constraints. Okay, so this has a number of applications in computer science as well, because it's tightly connected. So the fact that these two pictures are not equivalent is tightly connected with some basic theorems in information theory, like the asymptotic equipartition system, and also channel coding and other things. So I have to cut it here, but there will be other talks today by other people in our group. Thanks a lot.
It's fascinating how in several disciplines actually there are different formulation problems that in my vision I hope they will converge at a certain point. I think that what we are creating is something towards this convergence. Okay, so now we have Emanuele Salerno from CNR, and he will talk on exploring structure and big data for discovering information signals and images. So we'll have a different form of data in which we will want to discover some information. This is images. So there is meat for every taste.
Thank you, and good morning all. I am going to, rather than being specific, as many of the presentation these 2 days have been, I'm going to present a short overview of what we do in the Signals and Image Laboratory of the Institute of Information Science and Technology of CNR. Unfortunately, hearing many of the things that have been said yesterday and this morning, I think that I'm afraid that the most of I'm going to say will be completely useless. But okay, just take it as an expression of our point of view on data and on data science, and on some of the projects we are active in our quite large laboratory. Okay, this is totally useless, of course, but it is, I left it just to stress the importance of this kind of meetings. I copied the definition from the website of your PhD program that says that data science aims to turn data into knowledge, and the key to this translation is interdisciplinarity. Now, okay, it will be something to say about interdisciplinary and also on paradigm, of course, but I will focus just on knowledge, citing an undisputed authority in this field, which is Thomas Sennett, who was in 1934 was complaining about losing wisdom into knowledge and losing knowledge in information. Okay, these verses can be read in different modalities. I mean, top down or bottom up, and I could say that information processing gives knowledge, and knowledge processing gives wisdom. But okay, I will also overlook this aspect, and I will add a fake couplet to this poem that says, "Where is the information we have lost in data?" Okay, so continue the presentation. For example, we have a data piece here. This of course contains information. This is data. But I ask you, this one is the same data as the one that was shown in the previous image. This is also an image in a sense. And okay, I could say yes, because each colored dots of the first image is exactly mapped in an equally colored dot in the second image. So in a sense we have the same data in the two images. But of course there is something that is missing in the second image. What is this, this missing aspect? It's structure. In the sense that from the first image I have the possibility to extract meaning from the data. In the second meaning, no way, and no possibility to extract the same information from the data because the arrangement of the different pixels is completely random. So information associated with data also is also pertaining to structure. So what is structure in this case? Structure can be seen as order or mutual relationship between numerical values, or for statistics, correlations, dependencies, entropy, if you want. So, but this is not common, because we can also have different structures in data. For example, look at this image. I can extract information from this image in the sense that there is ordering, there is mutual relationships, correlation, and so on and so forth. But I can add something to this. I can assume that all the details of this image are taken from a superposition of different data sets. In the case, these different data sets are two different images. So I can model the structure also as a data generation process, which can be modeled. The model may be known, may be also unknown, and to discover. So another thing I read from your web page was one of the goals of data science is to discover unseen patterns in data. So which is the particularity of signal and image processing with respect to data science? Is to discover unseen patterns in data, taking structure into account. So we are seeing some examples of structure, but I do not want to dig into theoretical details. So this is also, in a sense, taken from your website, in the sense that this cloud of words are taken from the disciplines that are mentioned in your website as being part of data science. And I see here many important keywords such as meaning, learning, language processing, complex artificial intelligence, and so on. But I do not see structure, and I do not see either signals or images. So, which is the importance of this, of what I'm seeing? For us, signals and images are data structures, are data sets equipped with very strong structure. And this is why the IEEE Data Science Workshop for 2019 is organized by the IEEE Signal Processing Society. So data science is also relevant for signal processing, and equally signal processing is relevant to data science. And now, just an overview of what we do in our lab, where we do many things, but in general we are trying to extract data, extract information from data. The application can be divided into three main areas. One area is life sciences. Another area I define it as human activity and society. And a third, smaller area, is cultural heritage. And okay, I'm going to just show you some examples from all this list of applications that I don't mention. I just add that the researchers, all the people in our labs are computer scientists, engineers, physicists, and mathematicians that with their theoretical equipment contribute to solve the problems that are related with these applications. And this is the first example from life science, brain connectivity. This has been treated in 2 or 3 contributions in this meeting. And okay, to extract brain connectivity and to understand what is happening in our brains can be based on different kinds of signals. In this case, we have the electroencephalographic signals. On the left, you see a number of signals that are related to different experimental conditions. From those signals, it is applying signal processing procedure, it is possible to extract events. And from these events, one can, from each of these events in a single channel of the electroencephalogram, one can extract some complexity index, that is an index indicating the self-organizing property of the area of the brain related to that channel of the electroencephalogram. So applying this kind of things to a number of different channels, we can go to connectonics, which is reconstructing a functional network within the brain. So extracting functional connectivity and physical connectivity. This is one example. The next example, also for Erjan talked about this yesterday. It is to take as the input functional MRI, from which we have a 3-dimensional image. I can establish connection between different areas that are activated in different modalities as a result of different stimuli, and I can construct functional connectivity matrices, which are also related to the different modalities of functioning of our brain. On this, it is important to say that it has a perspective clinical applications, because analyzing these maps, people are able to learn something about the healthy or non-healthy condition of the patients. Look at those maps. We have a similar map here, which is similar because it is a map that indicates correlation between couples of different entities. In this case, we are in a completely different case. We have not to reconstruct a network, but we have to reconstruct a chain. We are in computational biology, and modern sequencing techniques are able to give us the probability that a single fragment of DNA is in physical contact with another fragment of the chain, even genomically very distant from it. So, on the basis of, look at that, there are small squares marked in the map, and this means that also those data have a structure. And exploiting that structure, we are able to reconstruct the chain, the 3D configuration of the chain, in the sense that we are able to compute the spatial three-dimensional coordinates of all the fragments of the DNA chain, and also their sizes, the physical sizes, and the fragments are represented by those bits connected by the lines, the colored lines. Also, for life sciences, there is radiomics, which is much closer to the clinical application than the other things I have spoken about. And okay, in the previous examples, I showed you analysis of data that are homogeneous, in the sense that the data come from the same, from a unique or compatible source. In medical imaging, we have many kinds of sources, and from all these kind of sources, e.g., EEG is not an image, but I don't know, fMRI, computed tomography, PET, and also other kinds of medical imaging, we can extract a large number of features that are that form a sort of radiomic signature that is joined with other data coming from genomics, from pathology, from all other clinical data to help precision medicine, which means being able to design patient-based, specific to the patient therapy, and also means to analyze its effects on the single patient. Now, on human activity in society, we have an application in structural health monitoring, using all these applications are using data coming from drones equipped with visual sensors. In the first case, we have structural health monitoring, in the sense that the operator of the system is helped by an augmented reality tool that helps them to locate faults into, for example, historical masonry, as in this case. In the second case, the drone is also equipped with a thermal sensor, thermal infrared sensors, which enables the operator to measure the temperature of power lines and to, helped by vision technologies, as in the first case, able to locate ill-functioning domain. The third application is in precision agriculture. Last example, in cultural heritage, we have here a document a manuscript which is written in 2 adjacent pages of the book, and you see that the writing is oriented vertically, and applying some signals and image processing technique, we are able to, as in the case of the 2 towers before, to extract an output where there is another writing in the sheet is visible and the other is has disappeared. Last example, here we have a very degraded manuscript. We are able to free it from the interference coming in each page from the bottom side of the page, so we are able to clean the image from the interference, and we are also able to separate different patterns in it, in the sense that with some statistical processing we are able to extract only the writing, to isolate the writing from in the page, and also to isolate the stamp in this case, in that page. Thank you very much.
Okay, so I think another important reality of a lab working on data-driven approach, and then of course then you can contact them for the research questions that so far didn't emerge very much. Okay, so the other question is other presentation. It's big data processing and machine learning for cloud computing and MSP infrastructure. Tommaso Cucinotta. I really pray the presenters try to give an idea of what might be research challenges for the students. Maybe only one, and then so that it is a vision that might be engaged for 3 years of work. Devi partire da zero? So he has to program now.
Un attimo la faccio la presentazione.
Ora fai la presentazione. He has to do the presentation.
No, it's fine. It's done. Sorry about this. Crashed just, you know, it's Linux.
It's a real.
It crashed just before coming, so I had to reboot. So, good morning, everybody. I'm Tommaso Cucinotta. Thanks, Fosca, for the presentation on the Real-Time System Lab, Scuola Superiore Sant'Anna. So, I'm talking about big data processing, machine learning for cloud computing and NFP. And so, just a minimum of background. So this is just one of the problems we've been dealing with just in this period in our lab, and I just selected this because, of course, it's probably the most relevant to the data science topic we have in this event today. Going to the engineering of network operators, of network functions, a big shift that is happening in industry is the one that network operators, which used to rely on physical equipment, and they used to size and to plan the purchases of physical equipment for dealing with the capacity needs of their infrastructures. So we are talking about the infrastructure that allows us, everybody, to call, to place calls, to use the internet, to use applications on mobile systems and everything that is needed. I mean, mobile as well as cable systems, so everything that is needed to run a network operator system. So they are switching into using a cloud-based provisioning of resources. So basically, they are moving into the use of flexible computing elements. So switching away from dedicated physical equipment, and that's also possible thanks to the convergence of some of the major technologies behind telecommunications. So for example, you will remember that once upon a time we used to have tripolar telephony plugs at our homes. Nowadays we have
those clips that resemble pretty much there are, you know, the telephony clips that are very familiar to everybody, and probably everybody's switching basically to voice over IP networking, so that means telephony based over IP networks. So the convergence towards IP networks is facilitating this migration towards, at this point, data centers, hosting applications, and so how can we build flexible data centers? You would have heard, some of you followed my course on cloud computing, but others know of course about cloud computing, and the idea is to use virtualization so that you can host basically everything. So in the particular settings of cloud operators, what is everything? Well, for example, network functions dealing with security, so functions related to firewalling, authentication, intrusion detection, functions related to load balancing of traffic across multiple instances, functions related to DNS lookup services, network monitoring, and of course all those functions specific to, for example, LTE and IMS, if we are talking about telephony and also cellular systems. And another particularly challenging trend is the one to apply NFV also to the radio access network functions. And those are the functionality that are just behind an antenna of a cellular network. So there is the base station, then there is functions, there is stuff that needs to be processed. So you need to process data coming from this antenna in order to be able to support all the telecommunication stack. And here in this context we have very challenging latency requirements. So it makes it not very easy to do. This is just a typical example. As you can see, it's nothing special. It's a picture taken from Wikipedia that shows the IP multimedia subsystem with you know, its many components. And so, just to give you a hint of the complexity of a system that allows us to call each other, we need each and every little box that you see in this picture, because there may be different telephony systems, they can talk different standards, you may have to integrate stuff that's been developed across different countries, different standards. When you need interoperability, you need compatibility across multiple operators. And luckily, we are still able to call each other basically all over the world, which is almost a miracle if you think about how many different organizations are involved into all of this for making it happen. So all these elements have to talk to each other, and as I was saying, basically many of these boxes used to be like physical boxes with some special connectivity and cables, and nowadays it's all switching to software. Just to give you an example, this happens just when you plug a voice over IP telephone over the network or the plug. So there's a registration process that involves the communications across multiple of these elements. So as you can see, these elements you have here on the vertical axis are just some of the boxes you can see in this diagram. This is relatively simple. This is one that is a bit more involved. So this is like Eric, Colin, Pat, and the two users are on different IMS domains. So there is a colloquium going on among many of these systems. What happens here? So when we start deploying these components over virtualized network infrastructures, you get all the troubles, all the problems, all the issues, all the nightmares that are typical of cloud computing: performance instability, virtualization overheads, multi-tenant problems, which happen even in a private cloud or a network operator if you start using that same flexible data processing infrastructure for doing multiple things. And there's been, for example, research projects proposed back in times about deploying users' virtual machines on the base station or deploying virtual machines on the coffee shop gateway. So just to give you some examples of how things can get very complicated. So you may get performance issues, and you have to face with elasticity and scalability in software, and this is for network operators something relatively new, because they used to plan capacity and everything based on their physical equipment. So they know, like, if I plan to acquire this many users in my number of instances on the fly in a few minutes. And so you can do a lot more things more dynamically, but you have to design control loops that make sense in this novel context. And still, you may have to, it's not like you can switch from hardware physical base to virtualized network functions in SNAP. You have to deal with all the transitory phase with which you have a coexisting legacy equipment with novel equipment. And you have to handle large users communities, so we need scalability in this context, and this brings additional problems. So managing a cloud infrastructure brings plenty of challenges. That are related, for example, to operations and troubleshooting. And these are some of the challenges that deal mostly with data. Why? Because in these infrastructures, you have normally large-scale monitoring infrastructure. So like on every host, you pull out metrics, which can be system-level metrics as well as application-level metrics. And these metrics are basically all we have in order to base automation, in order to build automatic software systems that monitor the infrastructure and are able to understand what's going on if there's a problem, and to fix the problems automatically. That's the key, because these are not infrastructures that can be handled too much manually through human intervention. Albeit human intervention will always be needed, and of course it's always there's always a key need for human intervention. But what sides are we talking about? Here I'm putting an example that is not NFV, but is in the field of cloud infrastructures generally. So everybody knows AWS, and albeit I've been an employee, of course I'm not disclosing anything that I learned while I was an employee. So this is based on a very big to the massive scale of AWS by T.P. Morgan back in 2014. That is basically history. Okay, so this person was building this estimate that AWS had something around 5 million servers across 13 regions around the world, with 35 to 80 data centers with at least 50K servers per region. And this can, if you make some calculations, basically you can consider that each server generates hundreds of system or application metrics per minute and per request logs. And you may have something like tens of thousands requests per second. So the per request logs are those lines you have to keep in a log file for each and every request you receive, in case you are doing something like that. So this brings us to an estimate. It's just a rough estimate of 14,000 petabytes per year for 5 million servers. But I can tell you that this guy in 2014 was really off track by at least orders of magnitude. So what can we say? So we have this massive amount of data. The challenge is how can we use it? So for example, this data tells us if a host has a problem, is not getting traffic, this data can tell us. If a host has a problem and is responding particularly slow to requests, this data can tell us. And here the challenge is to be able to use this data, because before you have a serious crash of the system. A serious crash means simply that at a certain point you start having the telephony system doesn't work in a geographic area. That's a crash. Or if you take the generalistic cloud computing view, it's okay, my website is not working, or maybe the system, the social network of my preference that I use every day. Today I had 2 hours down without this social network. So boring. That's a crash of the system. The whole point is to not get there. That is the challenge. We don't want to get there to when the system crashes and goes down with an outage. In order to do so, the key point is to apply real-time analytics. So not only diagnostic, predictive analytics, but real-time analytics and automated alarming, so that we can predict ahead of time what's going to happen and try to alarm and to undertake actions, possibly in an automated way, otherwise with manual intervention, so that we can fix the system before the problem becomes so big that users would be impacted. And especially in this context, we are investigating a particular problem in the NFV instead, so switching from generalistic cloud to the network function virtualization for network operators, in conjunction with Vodafone, the well-known network operator. investigation is based on analyzing these massive amounts of data coming from the monitoring data, coming from the 12 data centers across Europe, Vodafone, and 12 countries with NFV data centers, which have, of course, additional data centers per country. Being useful insights for root cause analysis, identify critical issues about to cause pain and operational issues. And in our ongoing investigations, we are deploying machine learning techniques and artificial intelligence for the automated analysis of what's happening in this NFV infrastructure, so that we can build a useful, insightful support for performance troubleshooting, virtual capacity management, physical capacity management and planning. So this is just. Thanks for listening.
You programmed the slide and you made the slide in 3 minutes. You are great. So now it's again an approach for complex systems. You see the variety that we have seen. So it's statisticians saying that we have to measure poverty. So then we saw images are another kind of, and scenes are another kind of data. Now, so we see the complex system analysis of the phenomena and the new way to measure. Stavo intrattenendo. And also the real time, so the algorithmic part, real time analysis. You know, I have an example of a very an example that I saw in a conference of online analysis. So when you, there is a person speaking, so at the television there is a person speaking, and the voice it's completely doubled, and then you see so you see Obama saying that he will transform, he will attack, I don't know,
fake.
So creating online fake news.
That's actually
Okay, hi everybody. Thank you for stepping in for this nice initiative. Yeah, this contribution is about, again, network theory, and in particular about network reconstruction and one of the application, which is estimation of systemic risk. Okay, so basically, what is network reconstruction? Well, basically, when considering financial system, the information that we have about the system is never known completely. So basically, we have only partial information, and due to, for example, confidentiality or privacy issues, that prevent us from knowing all the details of, let's say, an interbank network or, in general, a financial system. So we need a way, we need a method to infer what is not accessible from of this system. And this is why we need network reconstruction. Okay, so how can we do that? Well, basically, when we have only partial information, we must consider an enlarged set of configuration that are compatible with relatively little information that we have on the system. So we consider an entire ensemble of possible configuration, and the idea is to make the best possible use of the available information to reduce this large set of alternatives that are all probable. So what can we do that? Well, basically, we have to employ what is known, which are the constraints, to reduce all these set of configuration. So basically, we start from an original graph that we don't know completely. We consider only the partial information that we have are the constraints, and we move to consider this enlarged set of possible alternatives. The recipe to shrink this and to make the best possible use of what we know, well, one of the many possible recipes, the one that we employ, is the maximization of Shannon entropy. So basically we have this functional, we maximize it, constrained to the information that is known about the system. The results that I will show are based on this recipe, an outcome of this recipe. But of course, a possible project or an exercise, if some of you is interested, is try to consider different functional. So there are entire families of divergences, functional, for example, that may be explored to see if we can achieve a better reconstruction, if the functional form of these quantities can better employ the available information. This is something not trivial, that is already a possible avenue of research. So, what is network reconstruction more detailedly? Well, basically, we need to guess the entries of a matrix that represent, for example, an interbank network. So the entries are the exchange between banks, and you have to provide a guess of each of them. The information that we typically have is local, so we know, for example, the total number of neighbors of each bank, or the total number of countries I'm trading with, and the flux, so the total amount of money I'm lending or borrowing, total import or export. And those are, this is the available information. We maximize Shannon entropy with respect to this. Another possible question that we would like to answer is it possible to enforce different constraints, possibly not local constraints that try to capture something more complex, for example, cycles or triangles or more complex patterns. But if we still consider local constraint, the recipe works quite nicely, because here we have an example of a particular system which is INIT, which is the Italian market for the electronic market for Italian interbank deposit. On the left we have a snapshot of this system in 2003, so the real network. On the right we have a reconstruction, so the outcome of the recipe I briefly sketched. So it works quite nicely, especially if compared with the available reconstruction algorithm that have been proposed, that make, for example, produce two dense configurations, as in the first case, or two sparse configurations, as in the second case, or completely random structure that do not resemble the original network. Another aspect of network reconstruction is something which is, if you want, more local, which is link prediction. So, given a system, we may suspect that there are many connections that we don't observe, that should be there but we don't observe. So how can we try to infer this unknown connection? Well, the recipe is basically the same, maximization of that functional under the known information. And the outcome of this procedure is basically a list of score. What is the most probable missing link, and from the most probable one to the least probable one. So we have a recipe for spotting what are the most probable connections that we don't observe. Of course, there is another aspect of the problem, which is weight prediction. Even if we see the link, can we imagine we don't have information about the weight? Can we modify a bit the recipe to spot also missing weights? Again, with a recipe that, together with Diego, for example, and another PhD student of mine, together with these guys, we have come up with a recipe that so far works quite nicely, again, for economic and financial networks. The accuracy of the link prediction is quite high. But of course there is room for improvement, because the constraints, the information that is effective for the system may be not for social system, for example. In social system, triadic closure is known to play a role that is completely not considered here. So how can we extend this to different kind of system? This is another possible question. Again, this is another example, for the Dutch interbank network, and as I said before, two nice exercises could be, let's do more refined link prediction or weight prediction exercises by refining the recipe of entropy maximization. A third view about reconstruction is generalizing the same Shannon entropy function by considering, for example, conditional probability distribution. So trying to enforce some kind of prior information. What you're currently doing is basically treating prior information as information about the topology and trying to derive a recipe for weight prediction or weight reconstruction. But again, this is a very preliminary step that we have done to explore more complex functions. So, in a sense, this is another interesting aspect of to explore. And for what concerns the application of network reconstruction, of course, the best example is the systemic risk estimation, because it may happen, of course, that one institution in an interbank network fails, and we would like to know how the failure of this bank, for example, propagates, which are the effect of this failure. And of course, if we have a faithful representation of the network, we can provide a faithful estimation of systemic risk. For example, the percentage of banks that will be affected, that will fail internally. We can compare, for example, the observed value of some indicators of systemic risk, like the debt rank, for example. Network reconstruction is effective in reproducing these values, but we would like, of course, to do more to improve these. And in order to improve these, we have started to look at the different kind of properties, which are spectral properties. So by not considering local constraint, because the spectrum of an aviation symmetrics actually takes into account a much more global kind of information, is it possible, for example, to detect early movement of a financial system towards the crisis? So in a sense provide early warning signals of evolution towards critical configuration. Well, if we consider the spectral properties, in this case is the spectral radius, so the largest eigenvalue of this financial system, as the system moves towards the crisis, that is basically 2008, and the first snapshot is 1998, we see that the spectral radius becomes less and less compatible with the prediction coming from a null model. So the idea is, yes, we have a hint that these kind of properties can be useful in revealing some kind of interesting evolution of the financial system, but still this is a preliminary observation, so we can do more research on that. So just to sum up, there is room for improvement about network reconstruction and improving the current recipe. So including, as I said before, prior information, or even imagining a completely Bayesian framework for reconstruction from the beginning, or work on the spectral properties to not only detect early warning signals of some critical events, but also to design optimal financial systems. So design optimal structures, given the same constraint, what should be the best connection, the pattern of connection between financial institutions or banks. This is an answer this is a question we can answer with this. And at the end, well, the last question, extend the entire formalism not only to monopartite network, but to bipartite and partite networks, for example. So when you have several layers and you have connections only between layers and not within layers. So there is a lot of work to do here. All these results have been published in two reviews, one on Nature reviews, and the other one on physics reports. So if you would like to have more information, these are the references, and yeah, the questions are what we can work together with. Thank you.
So plenty of questions. You are confused, will be even worse in the afternoon, so you get confused, then you have time to metabolize all this and then take your time for to your own elaboration of what you have listened. Then Professor Pedreschi is open to any questions, so he's not here, so we can say, ask to Professor Pedreschi for everything. And okay, so now it's time to go to lunch, and as we are very late with the program, we are supposed to start at 2. Is it the problem is we confirm that having only 1 hour? Can you manage to do this in 1 hour? So that we will finish in time for the evening. Okay?